All right. So good evening once again, everyone. So in this session, we are going to discuss the topics particularly which are going to be there in quiz two. Mainly, it is 1 to 8. The syllabus is from week 1 to 8 with emphasis on topics from week 5 to 8. Okay. So that is how the weightage is going to be. And before I get to whatever I have planned, if there are any questions, I'd like to begin with that. Please go ahead and ask.
So, from 1 to 4, what topics is expected, sir?
I mean, similar to what you've already seen in quiz one, although this time it'll be less, like and the weightage is less there, right? Because mostly we're going to focus on 5 to 8, but still there will be questions from some 1 or 2 questions from not 1 or 2. I mean, it could be like it could vary, but not so much. Okay, so 1 to 4, week 1 to 4 also you'll see some questions.
You will get the due parts again, due parts and uh,
Well, I'm not sure. I'm not sure on that part. Yeah. Uh,
okay, okay,
okay.
okay, sir. Thank you.
All right, all right. So yeah, so again, so I think Vasu had put in a list of topics to discuss. Apparently, is not here yet, but I think we can start with that because that seems to be something that
Yeah,
people
that's
are
the pain point for most of us.
asking about. So one is subsumption, with regards to JCC, RCC, and CCC, and so on and so forth. Okay, so just give me one moment, please. I'll just share the other screen also.
So regarding subscription, I want to add one point.
Go ahead, please tell me. Yeah, please, please.
Yeah, sir. Actually, in week 1 to 4, we assumed the
Hmm.
subscription as direct. What is the link? So, for example, edge coverage we subsumes of node coverage, right? That's how we understood.
Edge coverage subsumes node coverage. Is that what you're
No,
saying?
no, no. Edge coverage subsumes node coverage. That's what I understood from the graphs which we saw.
Sorry, tell me, I'm not getting your the last point that you said. So you are saying
No,
that
no.
edge coverage? Go ahead, please.
Yeah.
Again.
So in week 1 to 4, we had subscription graphs, right, which showed
Right.
edge coverage and all. So that
Mm,
time you mentioned edge coverage subsumes node coverage. So
right.
top subsumes bottom.
Yeah, yeah.
Yeah, that way you mentioned. But
Right.
when I come to logic coverage criteria, the graph has been reversed.
No, no, no. So
Okay.
it depends on the arrow, no, that is given. Okay, I'll take a look at that
Yeah,
and mention that
just
again.
yeah,
Yeah.
just see that point. I think it's
So
been
the
reversed.
the confusion actually, sorry, confusion actually is with the subset versus subsumption. See,
Mm-hmm.
the subsumption is basically if if that particular thing is whatever the solution, then it will solve whatever it subsumes also automatically. But other way around is not true, right? So that
Yeah,
I
right.
think is a
Right.
confusion. Which direction is the subset? Which direction is the subsumption?
Yeah, yeah. So for that, I'll have to just share my screen with the slide. I'll just make that point clear again, once again. So the thing is, you have to pay attention to the requirement. See this, the idea of subsumption. No, okay, is the screen coming up? Like, is it visible or are you able to see this? Okay, I just close the another
Yeah.
screen. Okay, so the thing is, I'll go through both the slides. So one part was structural graph coverage and what we have seen, right? So here, I quickly show you the graph, the diagram rather. Uh, it's a subsumption and graph only. Yeah, this one. So you see, what happens is that if I am doing complete path coverage, then I am doing implicitly prime path coverage also. If I'm doing prime path coverage, then implicitly it does edge coverage. But note that prime path coverage does not subsume edge pair coverage, right? That's how you read this, right? So the arrow points downward, meaning that if I do this, then I'm also doing that and everything below it. Okay, so the top thing is doing the bottom thing. It's not about top or bottom. It's the idea is that the arrow is saying that, right? So you have this one that subsumes it. Subsumption is in the direction of the arrow. So complete path coverage subsumes prime path coverage. Now, what does it mean? Let's take a step back and understand what does it mean for something to subsume something. Subsumption means that if I do one thing, one coverage criteria, then let's call it T1, for example, right? So and T1 subsumes T2, right? So if you do T1, then you're also doing whatever requirements were there for T2, right? So that's what it is. Now, subsumption is with respect to the requirement. So, for example, What does edge coverage say? Edge coverage says I have to traverse every edge of the CFG, right? Isn't it something that prime path coverage is also doing? Because we compute the prime path, in all prime paths, all the edges are already there. They are present. So it is obviously understood that if I do prime path coverage, if I travel all those paths, I'll be covering edge all the edges as well, right? So the requirements for edge coverage are also being satisfied when I am doing a prime path coverage. Okay, so that's what subsumption means. So that is with respect to the test requirements. Now the confusion I think is coming in the logic. Logic coverage criteria is because you are considering the the subsets, or the set of pairs as the test requirements. That is not the case actually. So for that I'll go back, and is this part clear? Is this graph clear first
Yes,
of all?
sir.
Okay, so that is how it is. Now I'm going to go to the other part where we have mentioned
So
this. Yeah, go ahead, Vasu, please.
no, that's
Okay, so this logic one, we also have the subsumption graph. Oh, it's not in the summary. I think I have to go to the criteria. This one, yeah. So we have to actually, the point is, in this logic coverage criteria, the test requirements are not related to the subsets that we get, like the sets of pairs. Those are not related to that. Actually, we have to look into the requirements. I'll make that clear also. Okay, so before we get there, I'll just show the graph of subsumption, where it is. Yeah, here. Okay, so again, same thing, right? The direction of the arrows is still. So think about this. So this is like prime path coverage doing a lot of other things also. And that's how you read it, right? Same thing here is happening as well, right? So it's just similar. So you had complete path coverage, which is doing a lot of things here, right? Similarly, you do here combinatorial coverage, which is saying that I'm going to do every combination. Now, where are these combinations coming from? These are coming from the truth table, okay? So of course, you have finite number of rows in the truth table, right? It may be large, but then you have finite rows, right? The number of possibilities are finite. So you do all of it. Of course, it is infeasible most of the time, but I'm just telling that if one wants to do that, they can do it, right? So I have done all combinations from the truth table. Then of course, all these requirements, are from the truth table only, right? From those rows, right? We are going to construct pairs from the rows of the truth table. So if I do all rows, then of course I have covered the requirements for RACC, CACC, GACC, everything, right? So all combinations coverage does subsume everything, because everything that could come as a pair will come from the truth table only, and combinatorial is saying that I'm going to do all combinations. So certainly you have done every pair, like every pair you have covered. Okay, now where the confusion comes from is here, I think. So for example, so this is okay. I'll go one of the examples are there, right? Table, maybe this one, yeah. So this one. So what happens is, so first thing is GACC. Now GACC says, okay, that the active clause, let's say A is the active clause, I have to make the major and active, make the major clause active and then take the pair. So this is ACC, active class coverage, like general active class coverage, for example. So it says, what are the requirements? Okay, forget about the pairs for the time being. Okay, we are talking about requirements. So what it is saying, it's saying you make your major clause active. How do I make it active? By doing the XOR method, get the conditions and ensure that it is active. Now assume that it is active. Then I need to, there are two requirements, right? One is my major clause is true, right? While it is active, and the major clause is false. That is the only thing GSC is saying, right? So you get all such subsets, right? So for example, I'm not sure under which conditions it is active. Okay, this is CNF, right? Conjunctive normal form. So we have learned that in conjunctive normal form, you have to make all the other clauses true to make the one clause active. So if I want to make this active, A active, then I have to set B or C to true. Meaning if B or C either of them are true, then A is active. So A is active in which cases? I think, yeah, this is how you get it, right? B or C is the P sub A. PA is B or C. So this is how the active case, right? 4 and 8 we have removed because here it is not active. So this will not even be active class coverage. We are not going to consider that, right? 4 and 8. Yeah. So these are the active rows. So that first part is satisfied, like this is active. Now, what are the requirements? Requirements is, I'm talking about GACC. Major clause true, major clause false. And it is not talking about anything else. But to make it active, true ones, false ones. Okay, so isn't it happening in every pair. So then therefore I could take anything, right? I could take anything. I could take 2 with 6. I could take 3 with 7. I could have taken 1 with 7. Right? I just need to make sure one case my major clause is true, another case major clause is false. That is the only thing GSS is saying now. So therefore what happens is that you get a cross product of this and that. So you get 1 5, 1 6, 1 7, 2 5, 2 6, 2 7, 3 5, 3 6, 3 7, 9 GSS pairs. Okay. But the thing is, the key point here is all the GSS pairs, anyone is sufficient to satisfy the requirement. All of them are satisfying the requirement of GSSE. It is not as if you exercise all the pairs, then only your GSSE is satisfied. That is not the case. Okay, GSSE is saying that you have to make your major clause active and true case and false case. So I can take any pair then, right? I could take 1 5. That is also sufficient. I could take 2 6. I could take 3 7. Anything I could take, right? That is the idea, right? And then I have to do it for the next clause. That is the requirement. Part of the requirement is that you have to do it for all clauses. So we'll ask questions on only one. Okay, so you do it for A, true, false. You do it for B, make it active, true, false. You do it for C, right? So you do it for all of them. That is part of the requirement. But all pairs are enough to satisfy the requirement. Okay, it is not as if you are going to you have to have test cases for all cases, like all the pairs. For 1 5 and for 1 6 and 1 7 separately, you need not have test cases. Okay, any one pair is sufficient to do GSSE because it is saying that you have to make it true ones and false ones. So that is where the confusion comes from, I think. You see, it is saying that first part, you have to make it active. This entire, you know, sentence is talking about making the major clause active. So this first part is done. I have made my major clause active. Once it is active, there are two requirements, right? So subsumption, be it for graph, be it for logic based criteria, or be it for any other testing technique, the subsumption is always with regards to the requirement. Okay, it is not talking about how you are getting to that requirement, or what are the pairs and so on and so forth. It is saying what is the requirement. Is that requirement being fulfilled by any other criteria? Then I'll say yes. Then okay, then that criteria also subsumes the other criteria. Okay, so TR for GSS is saying for each clause you have to make the uh, you know of course you have to make it active. That's okay. And then CI evaluates to true and CI evaluates to false. Two requirements, just two requirements. Okay, so all pairs are doing it. 1 5 is also doing it, 2 6 is also doing it, 3 7 is also doing it, 1 7 is also doing it. Any pair I could take, so any one pair is sufficient to do GSCC. Okay, that is the idea. Now CSCC is saying the same thing, right? It is exactly saying the same thing. You have to make it active. Two requirements, again, requirements are only two, right? Pairs may be different, but requirements are always two, right? Make your major clause true, make your major clause false while it is active. But correlated is additionally saying something, right? It is saying that when you are flipping your major clause, you make sure that predicate also flips. Predicate must change in correlated active clause coverage, and therefore the pairs are different. GSSC pairs may be different from CSSC pairs. It could happen. It could be same also. It could be different also. But the requirement is satisfied, right? As long as the requirements are satisfied, the one criteria would subsume the other one. So by definition, CSCC subsumes GSCC, because this entire thing up until this point is exactly what GSCC is asking us to do, and we are doing it in CSCC also. So if you have pairs, if you have CSCC pairs, and you create test cases based on your CSCC pairs, you're also doing something that GSCC asked for. Like this is the entire thing. That the highlighted portion is whatever GSCC is saying, right? So if I do CSCC, I have done GSCC as well without even thinking about it, right? But it is saying something additional. So if you do add something, subsumption holds, right? You're doing additional. Okay. So that's what, like, it is as if I have asked for one answer about something, but you are giving me two correct answers, something like that, right? You are additionally doing something. So of course the lesser criteria will of course be done. That is subsumed because that's what you're doing. Okay, this part and that part is same in GCC and CCC. Therefore CSCC subsumes GCC. It is not related to the pairs. Okay, subsumption is with regards to the requirements are always two. For GCC there are two requirements only for each clause, of course, but for each thing is in each criteria also, right? GCC is also talking about each clause, and then you have CSCC, which is also saying about each clause, and then you have RSCC, which is also saying about each clause, right? And only two requirements. So TR has two requirements for each clause. Here also you have TR has two requirements for each clause, and GSSC also you have the same thing. So therefore we say that if you do CSSC, because that is additional, right? RSCC. So RSCC subsumes GSCC. CSCC also subsumes GSCC. Okay, and these two, the way we have defined it, not related. CSCC and RSCC are not related to each other. At least the way we have defined it. Okay, some textbooks do consider that RSCC subsumes CSCC, but note that in our case we are not saying that. Okay, the CSCC, as I've told multiple times, I think that CSCC subsumes rather sorry, CSCC is talking about predicate, talking about the predicate. Okay, predicate must be true for one case, false for the other case, meaning it should flip. Okay, that is what CSCC is saying, and RSCC is not talking about the uh, 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 predicate at all. It is not saying anything about the predicate. This activeness is always there, right? This part up until this thing is determination is there for everything, right? For active case, so we are not talking about that. But here it is not talking about the predicate switching. Okay, it is saying the minor clauses must not change. So you have the true case and the false case. When you are having this TR two requirements, right? So when you flip, when you go from true to false, the minor clauses should remain the same. Only those pairs will be considered as RACC pairs. But by the very definition, we can see that RACC subsumes GSCC because GSCC was saying something less than this. Okay, CSCC was not even rather GSCC was not saying anything about the minor clauses. Okay, but here we have an additional thing that is given. Okay, so that is the general idea. Is that okay? At least the subsumption part, is it fine? Or any more question in this regard? Kelvin, is this fine?
If you
Can
go
you
back to the
just
chart, the graph, the
Okay, so graph is here. Just give me
yeah,
one
at the
moment.
bottom.
Yeah, sorry. Keep that open maybe.
The GSCC, ideally, if it was on the top, would it have been better? No, nothing like that, right? No,
No, because
no.
this the other side. No, this other side is talking about ICC, right? The inactive
Acha,
copy.
okay,
So
okay.
yeah. No.
No,
So this is
I only look at it as whatever. See, whatever satisfies. If I have a
mm,
let's say a test requirement which is
mm,
satisfying GSCC, then it
mm.
will automatically satisfy clause CC. So that's
CC.
what
Yeah,
subsumption.
that's correct. Yeah, that's what
That's what
subsumption is.
subsumption means, right? So it's
Mm.
a smaller. So the moment you think about it as a subset, and because sometimes you have many more rows in GSCC versus CC, it gets
No.
confusing.
Yeah, I
So
understand. I do
I
understand.
think of it like that. It's like a smaller. It's like a stricter definition. So if that is
Stricter definition. Yeah.
that's
So
what
CSCC is
I'm
stricter
clear.
than. Exactly. So if you think about that way, it is less because it is strict. It is not as if it is more, therefore it will subsume. Okay, it is the other way around. Because it is less, it is subsuming because it is stricter in
Yeah,
this
it's
case.
usually lesser because it's stricter.
Yeah, I think that is happening because we are coming from graph coverage criteria. No, the complete prime path coverage has more paths. Therefore, it does edge coverage also. Edge coverage has less paths. If you think about it, right? Prime path is doing a lot more than edge coverage, right? And therefore, implicitly, it is doing edge coverage as well. But here it is the different thing. It is in terms of strictness, so to speak, right? It is having more. So therefore, it may be less also, but it's still subsuming, right? So don't get confused between the two. Okay, I think we have discussed enough on this
no,
one. Is it? Yeah,
yeah,
go ahead.
you want out. So subsumption is that it covers this one, right? That's the meaning of it.
And that's the meaning of it. Yes, it
Yeah,
covers it.
it covers it,
Okay.
right? So one
Yeah.
doubt. So if you consider CACC,
Hmm.
we are considering just the pairs where predicate is changing, right?
Right.
So I have a simple doubt is that. So
Okay.
let's assume a pair where A equals to true. P of A is default true for ACC. So let's leave it
Okay.
out. A
Okay.
equals to true and A
Hmm.
equals to 4, we have a pair. Okay.
Okay. Yeah.
But that pair has predicate to true for both the cases.
Okay.
Okay.
So that
It
that will
comes,
be
yeah.
just GSCC. It
Yeah,
will be just GSCC.
it comes under GSCC. Okay.
Yeah. Yeah.
Yeah. And it does not come under CACC.
No, it does not.
Yeah. But we tell that CACC subsumes GACC, right?
No, that's what I'm saying. CACC subsumes GACC, no, not the other way around. What the example you are giving is that of GACC, right? We never said GACC subsumes CACC. Okay,
No,
it is the
no,
order that
no.
matters.
The
Uh-huh.
example I gave where CACC does not have that pair.
Yeah.
Okay. GACC has that pair. Okay.
Yeah, that's what. So
Yeah,
in
that means,
anything,
yeah,
yeah. So CSCC is not done, but GSCC is done, right?
yeah,
That,
correct.
exactly. That's what we are saying.
Yeah,
So
then that
hmm,
means CACC does not subsume GACC, right?
no, no, no. I think you're not able to,
Yeah,
for some reason, get the point. Okay, so we'll come to this discussion maybe after some time. Tell me, is that okay? Because the
yeah.
other things
No,
also
yeah,
take
no,
over.
no. Previous age coverage you mentioned like that. Here it is mentioned differently. That's why.
Yeah, here actually it is because of the difference in the way we are, thinking about requirements. That's why here the requirements are different. You have paths, so it is implicit that okay, larger number of paths mean, all the smaller criteria are already being fulfilled, right? Because you have more paths mean more coverage.
Correct.
Here more paths mean more coverage. Here that is not the case. Here we have to look into the requirements, right? Here is a
Right.
different thing. It's not directly proportional to the number of requirements you have
Okay.
in that way.
Yeah.
Okay.
Yeah. So we say that GACC is covering CACC, right?
No, no, we say CACC is covering GACC. Yeah, the other way around. So you have
Okay.
CACC. See, if you do RACC, then GACC is done. If you do correlated, then GACC is done. That's why general. Okay, one way to remember it. One way to remember it that GACC is the general case. Of course, it says
Correct.
general, right? These two are specialized cases. So
Yeah.
just remember one thing. Okay, if you do a special case, general case is covered. Okay, so you have correlated special case, restricted the special case. All these two special cases are subsuming the general case always. Just remember like that. If
Okay.
you do general, you're
Okay.
not doing
Okay.
a
Okay.
specialized.
I got it. Subscription
Yeah,
means you meant here is that it is under this one, GCC.
yeah. Exactly. Jesus is under this one, right? Exactly. That's what.
Ah, okay, okay. I think then Master's point was correct. GCC should come at top and these two should come at bottom. Then definitely correct.
No, no, no. The arrow is this way, right?
Yeah,
Okay.
arrow is fine, but just to understand.
I think we are trying to correlate this with that, but those two graphs are different.
Yeah,
Okay.
fine, fine, fine.
By the way, okay, fine. So just remember this. So the general case is the general case. If you've done the general thing, you've not done the specialized thing. But if you do the special coverage, like these two are specialized requirements, having specialized requirement, right? So these two, if you do, general is done by default. Okay. Because you've done the special case, the general case will be done. Same goes here, right? So active class coverage is a special case of class coverage. So I've done the active class coverage, then class coverage is all automatically done. That's a special case, right? So that's how it works. Okay, I think we can move ahead. Yeah. So the next point that was uh, uh, yeah, go ahead. Somebody has raised a hand. I think not able to see the meet window. Can you point out your question, please? Okay, fine. So yeah, I will just stop sharing from here. Yeah, before we get there, so I think some. So Vasu, can you go ahead with your question, please? I think you had put a list, right? In that
No, I'm
list.
saying generally we discuss PYQs, and that question has come up across. That's like a collective question. It's not just my
Okay,
questions.
okay,
Like
okay,
that subsumption Telvin had, right. He was particularly interested in clarifying it, right.
okay.
So I had put all the questions. So if you want, I can read it out. I mean,
I mean it's okay. I think I have
But
it open on my part also.
you can carry on with ICC ones. That also we had on this.
Oh, ICC is it? Okay. So let me go through that also. Uh, yeah, I mean the best way is to look at the slide generally, but I'll try to do some example. Also, I have put in an example on discourse wherein it shows all that. So one may look into that also. But
It
yeah, since we
has
already
ACC alone, right? ICC was not there.
yeah, that example has ACC, but it has one pair where it is inactive. I think I'll have to add that paragraph saying that that pair is inactive. So okay, this one, right? So the inactive case, just let me yeah. So we have seen ACC, and after this the second part is, so correlated is done. So test requirements, be very clear on the test requirements. Okay, how many test requirements are there, where are those requirements, and so on and so forth. So inactive, what happens is, now we have seen active case. Inactive is the opposite of that in some sense. Okay, so it says, what was the prerequisite in active? You have to make it active. You have to make your measure clause active. PA being true. You know, you said that is always true in the active case. That is the precise point. Okay. So now here in the inactive case, we are saying it does not determine, meaning PA should be what? Should be false. Active should not be active, right? You could, I mean, one clause could either be active or inactive, at one point. So what we are saying is, in the active case, we have to make it active. That PA, PB, PC, all those denote whether something is active or inactive, respectively, like the clauses, right? So if PA is false, meaning A is inactive. Okay, so here that is what it says. In inactive, you have to make your clause inactive. That is the first part. That is the prerequisite. Once you have done that, then you have to cover for these four requirements under that condition. So in active case, we were saying you have to make it active and then cover for two requirements. Once it is active, you have to cover for true, false, two cases only, no? Two requirements. Here, there are four requirements after making it inactive. So inactive is one thing, like the prerequisite is to make it inactive. Once you make it inactive, then four requirements. What are those four requirements? You have to have the major clause, this is the CI is the major clause, true with P being true and CI evaluating to false. So this true false is still there, right? We have to still switch. That switch is still happening. But since it is inactive, we have additional thing here. We are saying that P being true. So one pair with P true, another pair of true false with P false. This is the major clause, right? So major clause true false with P true, major clause true false with P false. Okay, that is what happens in inactive. Is
Afnan,
that okay?
so
Go ahead.
the pair will be 1, 2, 1, 3, 4 alone, right? There will not be pair like 1, 3 and 2, 4.
No. That cannot be a pair. So 1, 3 cannot be a pair. Okay, you have to like the pair is this only. Under the case when P is true, true false. Under the case when P is false, true false for the major clause, respectively. Is that okay?
Okay.
Now, so this is what? This is general again. Similar to how we had general active, this is general inactive. A general inactive says that the values chosen for minor clauses CJ may vary, right? Here we are saying that it may vary. We are not concerned about the minor clauses, right? There are three things, right? In general, one is the major clause, other is the predicate, and the third is minor clauses. So everything other than the major clause is minor clause. All of us know that, right? All the other clauses are minor clauses. So what we are saying is that when I switch from one, like I'm considering these requirements, right? One, two, one, two. So I'm switching, right? From true to false. When I switch, I don't care what happens to minor clauses in the general case. P is true is okay, like that is part of the requirement, no? But when I flip, I'm not concerned about the minor clauses in the general case, right? This is the difference between GACC and RACC also. In GACC, when you are switching, you're not concerned about, what is happening to the minor clauses. Similarly, here we are not concerned. But the RICC, restriction is on the minor clauses. Restriction is on the minor clauses. So it is saying when I flip, you know, uh, the minor clauses must remain the same. So true to false, when I'm having this pair, right? As you said correctly, that P1 and 2. So 1 and 2, when I'm flipping, it should be remaining the same. 3 and 4, when I flip, the minor clauses should remain the same. So this is restricted. And then we don't have a correlated inactive. That is not possible. Because why? Because it does not determine P, right? If something does not determine, if the clause does not determine a predicate, it cannot be correlated. For correlation, determination is the necessity. Okay, for correlation to take place, it must determine. If it is not determining, then it cannot be correlated, and therefore we don't have CICC here. We just have GICC and RICC. Okay, I hope this distinction is clear between GICC and RICC. It's only about the minor clauses. Hopefully that part is clear. Is that okay? Tell me.
Yes, Afnan. It's
Okay, go ahead. Okay. Anyone else? Any other question, or shall we go ahead with the other part? Okay, so I presume it's fine. So going by the list that was given, the next thing is, and I'll have examples also. I'll try to, maybe not for the logic case, because logic, it takes a lot of time because we have other things to discuss also. For logic, example for logic coverage and all, we have discussed so many times, so you can go back and check that. But for other things, I'll try to have examples also. And meanwhile, if you have questions from PYQ or anything, just feel free to put it forward. We'll discuss all of that. Try to discuss as much as possible today. So now all depth coverage, all users, and all due paths, right? These three is the next point people are asking about, right? Yeah, so that could be done. So for that,
I can show a question if you want.
yeah,
You're
please
just
go ahead.
following
Go
something
ahead.
right.
Yeah. Go ahead.
Just give me one. Guys, I just assume that these are questions everybody wants based on some discussions yesterday.
No,
So
that
others
is
also
okay.
please chip in.
Hmm, hmm.
Just give me 1 second, sir. Just pull
Yeah,
out the.
yeah.
Uh, Already paths.
By the way, we are hoping for another session, rather, for specifically for problem solving. Like this one, I'll try to also cover as much as possible. But on 31st, we try to schedule one.
Can you see my screens?
Yeah, this one, yes, yes.
Yeah.
After,
So
sorry to interrupt.
Go ahead, please.
Yeah, for in GCC will subsume RICC, right? DACC will subsume RICC, right?
GACC, no, GACC does not like the active and
it's
inactive. They are not related. The assumption
No,
is
no,
not.
no, GACC will subsume RICC.
No, the other way around. RICC is the special case, right?
Okay,
So RICC will do GICC.
okay,
Always
yeah, fine.
put the other one on top. Okay,
Okay,
if you
fine.
want to think like that. All
Okay.
right, all right. Okay, yeah, go ahead, Vasu, please.
yeah. So this is one of the sample questions
Mm-hmm.
we were solving yesterday. Sorry, right? So the question is, which of the following criteria does a set of paths satisfy for the variable x? Okay.
Mm.
So these are the paths which are given. So there's a little bit of confusion on def coverage uses and all du paths
Yeah.
coverage.
So
Right? So
if I may interrupt before even getting there. So this is supposed to be all devs only. These two. I mean, yeah, this is correct only. No, other there was this question wherein we had mentioned all users, but it was not all users actually. This is correct. This is correct.
okay.
So this is
So
all devs only. So yeah, I'll try to. So can I take a snap of this graph only?
of
Is
course,
that
of
okay?
course, of course.
Yeah. Okay. So I'll take it and then explain on top of it. So.
So I've understood that this is the like this is given as the all def coverage, right?
Mhm.
And then if we add this 1, 3, 4, 6, 7, that will become all users coverage. But then
Mhm.
what is all DU
Due
paths
paths.
coverage? That's
Yeah.
the
Okay. So no, if I may speak and you may understand it, that is easy, but I'll also show you. But the thing
yeah,
is,
yeah. Go ahead.
all due paths, what happens is, see, the first thing is all defs. All defs saying that you have to reach all users, rather, sorry, all defs. Okay. You have to reach all definitions for a specific variable again, right? So we are talking about X here. So all defs is saying you have to reach all definitions. That is easy enough, no? As the name says. All
Correct.
users saying that you have to go through all du pairs, because of course you're always going to start from a def, right, and go to a use. So you're saying all users, meaning I have to go to all users. So if I go to all users, certainly I must have started from one def, right? So for every use, for every du path is just that, right? Def to use path. So if I'm saying, that's what the coverage name of the coverage says, all users. So if I'm reaching all users through all definitions, and this happens through all definitions, right? So then all users subsumes all defs, because I'm of course going to start from all different, like for every definition, right? So I'm going to go to every definition and then go reach every possible use from there. Like let's say
Hmm.
there's this definition at one, right? So for y, for example, I'm just giving an example, right? So y, so I'll from one I'll go to 1, 2, 1, 3 and all that. Like every use, I'll try to reach all users, whatever is reachable. I try to reach all users through all definitions. That is all users, right? But then what is all due paths? That's what you're asking, right?
Yeah.
Yeah. So if you understood the first two, see, all definitions, we don't talk about how do we reach something, right? We just make sure that we reach all users, all definitions at least once. Similarly, in all users, we are saying that we have to reach all users at least once. We are not saying how do we reach, what path to follow. We are not saying that. In all due paths, however, we are saying that you go to all users, of course, through all definitions, right? So for each definition, reach all users, and then all due paths is saying on top of it, through all possible paths. Because for some users, there are two paths to reach the same use. Okay. So what all due paths is saying that you have to exercise all paths to reach that use. Does that make sense?
Yeah. So see, the first two make sense completely. See, first is we are saying in the first one we have to reach all the definitions. So if I take this first one, the
Hmm.
definitions are here and here, right? So I'm
Okay.
reaching 1, 2, 4, 5, 7, and
Hmm.
then I am the other one is 1, 3, 4,
4, 5, 7.
5, 7, right? So both
Yeah.
these definitions are being covered at 2 and
Hmm.
3. So this is
Hmm.
definitely all def,
Okay.
right?
Very
Now,
nice.
is
Hmm.
this all uses? We don't know. We have to check, right? So
Yeah.
all uses are here and here, right? So six
Okay.
is not being covered. So this is
Hmm.
not all uses. right?
Not
So I
only
need 1, 3, 4, 6, 7,
six
for
them.
example,
Yeah, yeah,
or
yeah.
1, 2, 4, 6, 7 also would have been okay. 1, 2, 4, 6, 7 also would have been okay. Then I would have reached all uh, all uses, right? Now, but the thing is that the then you're saying that I can, so I can do 1, 2, 4, 5, 7, 1, 3, 4, 5, 7, 1, 2, 4, 6, 7, 1, 3, 4, 6, 7. So this entire all combinatorics will be your all du
All
paths,
due
right?
mass. Yeah, yeah. In fact, I think I might have lost you in between. So you said that 1, 2, 4, 6, 7 is one path, and 1, 3, 4, 6, 7 is another path for all users. But that is not the case, right? You have to
No, no,
go to 5 also.
either of them is
No, no, no.
okay.
No, no. Because what about 5 then? 5 also you have a use for X. I'm
No, no,
talking
I'm
about X.
saying, yeah, yeah, no, no, I'm saying I have this 1, 2, 4, 5, 7, 1, 3, 4, 5, 7, right?
Hmm.
If I add either 1, 3, 4, 6, 7 to this, or
Oh,
1, 2,
okay, okay,
4,
okay.
6,
You are
7,
okay. In addition
then
to.
it
Huh.
becomes all users
All users.
coverage,
Correct, correct, correct. In
right?
addition to the existing paths. Yeah, because 5 is already covered. So you are adding for 6 also.
Yeah,
You're adding
6
for 6.
also. Yeah.
Yeah, yeah. That
So
works. Hmm.
that, yeah. So or even if I have 1, 2, 4, like for example, if you take this, if I take
Hmm.
1, 2, 4, 5, 7,
Hmm.
and 1, 3, 4, 6, 7, this is also
Hmm.
all users coverage,
Yeah, this is also all users coverage. Yeah, yeah.
right?
That will help you in
Yeah, if I
distinguishing
just
between
change, correct, if I
hmm,
just change this 5 to 6, I will get
hmm,
all
hmm,
users coverage.
all
But
users.
for
Yeah,
all du paths now, it is basically almost like combinatorial coverage. Like I have to go
yeah,
through
yeah.
all the paths.
All the paths. Yeah, all users through all possible paths. That's what it says exactly on the slide.
Okay, 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 okay.
Okay.
Good.
Okay. So I
Anyway,
think
I'll give it over to you. Hand it over to you for explaining further. I mean, I've
yeah, yeah. I mean,
understood,
it's okay
but
if yeah, yeah. So if it is not, I mean, it's clear enough. Then I'll not go into that. I mean, it's fine.
no, it's clear for me. For the rest, I don't know. We should
Yeah,
ask.
yeah, yeah. Go ahead. I think if anyone else is having any doubt in this regard, yeah, Chandan, go ahead, please. Go ahead. Yeah.
Yes, so my doubt is like, in use coverage, my voice is very harsh today because of cold and off.
And it's okay. No, no worries. Yeah. Go ahead.
So there are two types of uses. One, we write the something like equation at the vertex or node,
PUs, PUs
and
and
yeah, and something we
uh-huh.
write on the edges.
No, that is yeah. On the edge is PUs, predicate use. On the node is CUs, computation use.
Okay,
Okay.
so both uses could use, right?
Both users, yeah. All users are users. So when you say users, it means all of them. Like regardless of whether it is on the edge or the node, you're going to go to all of them. Okay.
Okay.
Okay. Fine. So yeah. Yeah. Anyone else? Any other question? Um. Okay. I think it's fine, right? Okay. So I'll go to the next one on the and yeah, and don't worry. I mean, like if something comes up, no, in the middle of another discussion, you may note it down. Maybe put it on the chat, right? We'll go through all of them again. So
So
sometimes it
how do
happens that you're
we?
not able to ask questions because you don't have it at this moment.
I
But it's okay. Yeah, go ahead.
I have
Please.
another this thing. Like, how do we? Uh, I had
Mhm.
a follow up question on how do we? In one question in a PYQ, we had this: how do we identify the DU paths? Right? In a piece of code was given.
Okay.
I uh, no, sorry, I'm confusing matters. One second. One second. Uh, just give me
It's okay. It's okay. Yeah.
Sachin. Till then, somebody else can ask any questions. Yeah.
Yeah.
So,
Okay. So we'll go
yeah,
ahead
so
with others.
yeah, yeah, yeah. I'm just searching for it.
Uh, so and what else? So. You have, yeah, one thing is, straight away I'd like to point out the symbolic execution tree. No, one of the questions is that how do we know how many nodes are there, right? Because
Yeah,
sometimes we had this question, right? So no, the thing is, it is actually possible to do the symbolic execution tree for one program, right? So you have one code segment. If you do the symbolic execution tree for that, right, it is possible to do it in at least two ways. Okay. There might be more ways that we are not aware of. At least I'm not able to recall at this moment, but I'm sure that there are at least two ways of doing it, right? And therefore, it may cause a discrepancy in the number of nodes, because people might do it in two ways wherein you have a difference in the number of nodes. Okay. So we had actually way back in one of the earlier terms, we had put this forward to the professor, and she mentioned that it is indeed correct, like both ways are indeed correct, and it is causing a difference in the number of nodes. Okay. Therefore we decided not to ask this in the exam unless the symbolic execution tree itself is given, right? That then there is no confusion about how many nodes are there, right? But then if the only the code is given and the symbolic execution tree is not there, then we are not going to ask how many nodes are going to be there, because it may differ. Okay. So I think that'll help for those of
yeah,
you who have
yeah, yeah. I
concerning
got
about it.
the problem. So if I can share,
Okay.
actually, two not connected, two problems. First is this one, which is if you can see my screen.
Huh.
How many DD paths are there?
Okay. Okay.
Okay. Now it's from an old paper. I don't know whether this will like they're in
Mm-hmm.
circulation or not. But this is one question. And the second question I have is there was this code from
Mm-hmm.
which they said what is the complexity? That's okay. But then they said how many prime paths are there? So
Okay.
I constructed the graph and then
Mm-hmm.
tried to get the prime paths, but it's not matching. So I'm not sure whether it's the right way to do it. How do we think about this?
Oh, okay. Okay.
These
Quite
are the
old
two
paper
problems.
though. August 2023, right? Okay.
Yeah,
Okay. Hmm. Okay, go ahead. So I think we can clarify one by one. So the
yeah.
DD path, no, and DD path has some conditions, right? What could be considered a DD path? There is a condition, like there are some conditions, some criteria that for something to be considered a DD path, it has to satisfy certain things, right? Now it turns out that sometimes some nodes are falling into multiple buckets, right? I mean,
Hmm.
okay, so this could be a DD path because of reason so and so, reason one, and at the same time, this could also be a DD path because of another reason, reason two, right? So I mean, two reasons for something to be a DD path. Okay. So when we say number of DD paths, you can just classify it into any bucket, right? To say that okay, this is DD path because of this reason, then I'm counting it as one. That's okay. That works. Okay. Now the only thing is that you have to be careful about what conditions are there and where they are applicable. Okay. The only problem that occurs is because of something known as chains. Okay. Chains, the thing is that if I'm asking for you for the count, right? So you go through every node and try to see, okay, whether it fits this, requirement or not. If it is fitting, then you say, okay, this is one DD path. Then I'm counting it, right? So I go to the next one. Okay, is this fulfilling the criteria? You say yes. So then you're counting it and so on and so forth. The thing with chain is when something becomes a chain, right? When it is satisfying something, some portion of the graph is satisfying the criteria of being a chain, maximal chain to be precise, then that itself is a DD path, right? So then you are going to consider it as one DD path, right? So two nodes are there, and then you consider it as one chain. So and independently also those two nodes are being DD paths for some other reasons, right? That could happen, right? So when you consider it as a chain, then there is a discrepancy in the number of DD paths you get, right? If you consider it as a chain, then that is only one DD path. Whereas if you consider them independently, then there are two DD paths. You understand what I'm saying? Because it is happening and it is going to both, it is fulfilling both criteria, right, of being DD path. So then what we are saying is, if something is becoming a chain, right, if it is something is becoming a chain, like it is satisfying the criteria of being a maximal chain, then do consider it as one DD path, and we are going to count it as such only. Okay, even though within that chain, and the nodes may be fulfilling other criteria of being DD path, because of which independently they are DD paths also. Okay, but don't consider it when something is becoming a chain. Do consider it as a maximal chain only. So that is like a precedence that we are giving to chains. Okay, so with this
So
with this
if I count chains, then I get five of them. Like as in, it's just for me. Then it is a very straightforward thing, right? Like for example, one, two, three.
mhm,
Uh, this is one, right? One,
mhm.
two, three, four, six. Then one, two. Uh, so one, four, five, three, six. Right? One, two, three. Uh, so if I count all the independent, like I don't know how to say it. I could have written it
Yeah, yeah,
actually.
yeah. All
It would
the
have
unique
just
chains.
been so all the unique paths, if I count, I get 5.
So then, yeah, that's okay. That's what we are saying. So we are giving precedence to chains. Something is
But
promoted to be a chain.
they don't have to go through all the vertices, right? They don't necessarily have to.
No, no, all the vertices is not the point here. You just have to go through the graph independently and see what portions of the graph, what segments of the graph are becoming, are considered a DD path. Like for example, I'll just give you one example. So, for example, the final node is one DD path independently, regardless of whatever is happening, right? So you've got 6 here, I think, no, the last one, yeah. So
Yeah.
that is a DD path. Like that is itself a DD path, standalone DD path. Okay, one is a DD path. Like the node itself is a DD path. Okay, but then so when you consider chain and don't count 1 and 6 separately. That's what we are saying. Okay. Does that make sense?
Yeah. So for example, if I take a maximal chain here, I have 1, 4, 5, 3 cannot be 1, 4, 5, 3, 6. Is that a chain?
Yeah, all the internal nodes may only have the in degree and out degree as one, which is not happening, I think, with 3, no?
No,
3
it's
has
not
out
happening
degree.
with 3.
Yeah, so you
Yeah, it's
cannot
not
consider that
happening.
as, yeah. So you have to take independently then. I think 4, 5 is a chain, certainly, independently. 4, 5
Okay.
is a chain, is a maximal chain, uh,
So
and
this
and
is
1,
like
2,
how to
1,
approach
4,
this also is a little confusing, sir, actually.
yeah. Yeah, 1, 4, 5 cannot be a chain. Why? Because we said internal vertices, all the internal vertices must be, having in degree and odd. Yeah, internal vertices must be having in degree and odd degree as one. So that is also fine. Like 1, 4, 5 could be a chain also. Like see, the starting vertex and the ending vertex, we are not concerned about that. Like in the chain, whatever it starts with, whatever it ends with, only thing it should not be a loop, not be a loop. Meaning the initial and the final must be distinct. Okay. Final not in the sense of the terminal node. I'm not talking about that. Final in the sense of chain, like what is the last node in the chain. So the last node in the chain, the first node in the chain should be different. That is one. The other thing is internally, like after that, anything that comes up must have an in degree of one, out degree of one. Like both conditions should be true. Okay. So for example, 1, 4, 5 could be a chain.
Yeah, 1, 4,
And
5 is a
even
chain.
I think even you can go up to 3, right? Because we said internal nodes must be satisfying that criteria, right? So 1, 4, 5, 3 is one chain, isn't it?
Correct.
Yeah.
No, in this case, 1, 4, 5, 3 is a chain,
Hmm.
and we'll count 1 as an starting node, 6 as an ending node, and
Okay.
decision nodes has 2 and 3. That's the lead.
Ah. Okay. So here you are counting the node as okay. So you are counting this node as initial and final as independent DD pass, is it? Okay, because 6 is either way it is not considered like that. Okay. So
Yeah,
we'll have to make an
actually,
exception for that.
actually, a criterion for DT path should be written in the reverse order. They are out in
Hmm.
straightforward order. So we have to
Hmm.
first consider the chain, then go one by one. Then it will be easier for us to understand.
Okay.
That's the trick I
Makes sense.
found.
Yeah.
So would you be able to solve the paths for the DD paths for this and give it? If not now, later on discourse, can you put it? If you want, I can.
Yeah. I'll put it forward. That is done. That is for certain. I'll do that. The only condition where I mentioned, no, the only condition where precedence happens with chains is maximal chains is that when something is satisfying both criteria, right? There are two nodes. That are there, and both of them are becoming chained together, but independently also. Like for example, 4 and 5 is a good case, right? 4 and 5. So 4 and 5 is a chain, like independently. That's okay. But
But it's not the
but
maximal chain.
yeah, it's not the maximal chain, but that is another point. But I'm saying that even in maximal chain, if something is a maximal chain and internal nodes are satisfying some criteria of being a DD path, then you don't consider the internal nodes separately. That's what I'm saying. That's the only thing that I'm saying. Okay.
Yeah.
Right. Hmm.
So when we do 1, 4, 5, 3, we don't consider 4, 5 separately.
Yeah, 4, 5 separately, we don't do that. But 1, we have to consider it, and 6 also we have to consider it, as Tevin pointed out. Because it is not because 1 came in the chain that you don't consider 1 separately. You will have to consider it. Because apart from this, see, apart from apart from the starting and the ending in the chain, 1 does not fall into the criteria of being DD path independently, except that it is the initial node, right? So you have to consider that. Like the thing is, which node is becoming DD path because of what reason, you have to understand that. Okay, that is the only crux of this question. 1 is happening because it is the initial node, 6 is going because it is the final node, 4 and 5 are happening because 0.5 won't happen because that is not the maximal. So we'll have to extend it. So we extend it, we see 1453 becoming a maximal chain, right? So you consider that. 2 is becoming because of different reason. 2 is becoming DD path because of the fact that it is out degree of 2 decision vertex, right? So the decision vertex, you're going to cover that separately, okay? So that's what happens. Yeah. All right. So you have to think about
Okay.
which criteria it fulfills. Maybe I'll solve this one also and put it out on display.
Yeah, I'll put this one. If you can tell us like what mistake you made, I can try again, or you can solve it for us.
Yeah, I do understand that there's some gray area in the way we have defined, like we have mentioned on the slide, the definition for DD path. So maybe we'll have to improvise that a little bit.
Yeah, it's yeah. So this is the next question I had a doubt
Hmm.
on. This is, I think, my last question. So here it's given a code and it's asked for complexity. Complexity is simply there is an if, there is a for, you take 1 + 1, you add
Uh,
one more to it. So
one more to
complexity
it, yeah.
is 3. Yeah. Then it says, find the number of test requirements for prime path coverage. Right? So we have
Okay,
to identify the prime paths. Okay.
okay.
So I first drew the graph for this.
We have to check if the graph is okay. So one is
Yeah,
there and one
I'm
is,
guessing that because I'm not getting the right answer. I'm guessing that's where the mistake is.
yeah. So you
I
have, just give me one moment, I'll check that. So one
sure.
is there, so you're checking it from the if itself and you're considering the initialization. Okay, so that happens, and if okay, if it is less than, okay, if less than 1, then you're going to just less than equal to 1, then you're going to go to 3. 3 is the final. That's okay. If that is not happening, then you go to 2. And 2 happens to be okay. Okay, so you are starting the loop itself there. Yeah, that is okay. That should not be a problem. And if it is happening, then you go back again to, oh, okay. I see where the problem is.
See, from here,
See,
actually, in the program, I don't see if there is n is
huh,
greater than 1, it is going directly to return f, right?
the 1 to 3, this edge, right? One from 1, 3, this
1 to
edge.
3, yeah.
Yeah.
So, but if it's not, if
Hmm.
n is not greater than 1,
Hmm.
uh, sorry, if n
Greater
is
than 1.
sorry, if n is not greater than 1, it directly goes to 3 and returns f. If
Hmm.
n is greater than 1, basically if n is, let's say, 0, it or 1, it goes to 3 directly.
Hmm.
Otherwise it goes into this loop and
Loop. Yeah.
does whatever,
Yeah.
right?
So the problem is, see, the problem, your CFG has a problem. CFG, your problem is that from 2, from within the loop, once you do that, no, f into equal to I, that thing, when you do multiplication, you are going to 1, which is not possible. You cannot go to the, first node. You have to have an intermediate node in between, because see, in the program, what happens after you do f into equal to I, you come back to the loop, no, and you don't go to int f is
Yeah.
equal to 1. Here you're going back to int f is equal to 1, no? 1 is representing that, the very beginning of the, you're checking the condition again. You're not doing that, no? If you go back to 1, then you are checking n greater than 1 again, but that's not what you're
You're
doing
not
here.
checking. So the graph has to be read. Okay.
Yeah.
So I'll have to have a 2 here. From 2, I
Yeah.
go to, let's say, a 3, and then the
Yeah.
loop comes back to
Yeah.
2, and this, let's say, is a 4 or something like
Yeah.
that.
Then
Okay,
it'll come out to be correct.
let me do that. Let me try that. Maybe I'll
Yeah. Okay.
get it right. Okay, that I
Okay.
think that's all from my side.
Oh, okay.
So
All right. So yeah, any more things that we are going to discuss? Yeah. So actually, 31st, no, Thursday we are going to have a session wherein we'll specifically maybe take one of the PYQs and
the
go through that.
Thursday, actually, we have many of us have, I don't know the overlap, but Thursday 31st we also have LLM, we have session, and I have statistical computing. I'm sure
Oh,
others also have like that. So if possible, a Friday, if it's okay to, or you can just take a poll or
no,
something like
Friday is fine also, but then
Friday
Friday
I
somebody
have
mentioned
DL
that
session.
DL, yeah, DL is there, so that's why a lot of soft revision sessions are happening. But regardless, we'll try to, uh,
that. So you'll do it at this time, is it, sir?
yeah, 8:30 is fine, no?
Ah,
Or
okay. Let's okay. That's fine. Let's 8:30 is fine. 8:30 is
yeah,
fine.
8:30 is fine, right? So yeah, Thursday 8:30 we'll do that,
Okay,
because
sure,
there,
sure.
I mean, especially because of uh, you know because of popular request. So we have to go through that.
Okay, sir.
Yeah,
Thank you.
execution tree is done. Decision table. Yeah, decision table is number 5 that you put in, was to decision table and constraints. that okay? Or I'll go through symbolic though.
Yeah,
Symbolic.
as a concept, I was not clear as to how you're able to combine using decision tables.
Okay, so two things I'll go through now. One is some things in week 7. Though we had a detailed lecture on week 7 already, so that is there. Like if you want to go through that, you can go through that as well. But I'll go through the key aspects, like how to solve questions, particularly regarding that. What could be asked? That is one. The in week 7 symbolic execution, symbolic and concolic both, path constraints and so on. And week 8 also. Week 8 you have this input space partitioning, right? So I'll just touch upon that and see where we can get from there. Okay, these two things I'll cover now. Right, and then the last point is number 6 is you're saying propositional logic versus predicate logic, which is
That leave it. That is my personal question. Later,
okay. Yeah, so
I'll write
yeah,
it.
we'll discuss in one
I'll
more
yeah, I'll write it on
discourse. Maybe it's better
discourse.
to.
Yeah. It's
Okay,
not relevant.
okay, very good. So that covers for most of it. Now let us quickly go through, and this will cover one of the questions from Telvin also, who was asking regarding the GA question, right? So how it is done,
Yeah.
symbolic execution. Okay, so I think I have shared a tab, which should not be the case. I have to share the window. You can see the slide also. Okay. So week 7, see week 5 and 6 regarding logic, most of it is, so week 5 is active class coverage, week 6 is inactive. So we have discussed so many times now. And the specification, there is nothing much. I mean, you can just go through that by on your own. FSM, there's only one thing that you need to be aware of. That is the notion of acceptance, like what the FSM accepts. Okay, that was I think prior to this, the other discussion, yeah, graphs and FSM. So this one, if you want to revise once, that'll be good. Like what strings could be accepted and so on. So we have done that discussion earlier also. Okay, so after this we'll go to symbolic execution and see what all is there quickly, the key aspects. So the thing is, symbolic testing is, in a nutshell, it is trying to automate the process of exploring all paths. So you have a program, you have seen CFGs, you have seen data flow graphs and all that. So you understand, I think by now you appreciate that programs are they are graphs, right? The control flow of program is like a graph, and therefore we could have paths, execution paths, right? So all this prime path and other such paths. What are those paths? Those paths are basically execution paths, right? Like the test paths are execution paths. It starts from the first node, goes to the final node, and so on. Right? This is one execution path that I trace onto the program. So I give an input, and that input is going to follow a path in the program. I give a different input, maybe it is going to follow the same path, maybe it is going to follow a different path. Okay, so the idea of symbolic testing then, because you don't know, right? I mean, arbitrarily, I'm going to give an input unless you trace it by yourself, right? So I'm going to give an input, there's some complicated function I'm going to give an input. I don't know what path is going to be followed, right? Maybe I give a different input, maybe the same path is going, followed. Maybe a different path is followed. I don't know, especially for large code bases, right? You don't know what is going to happen once you give an input, right? So symbolic testing, what it is trying to do in a nutshell is trying to automate this process of exploring, going to all paths. So it is not randomly going anywhere. Like there's an algorithmic way of systematically going through all possible paths. That is the idea in symbolic testing. Okay. So yeah, basically analyzes, to determine what inputs cause each part of the program to execute. And why we are interested in doing so, by the way, because see, if we follow all paths, theoretically at least, then in some paths there might be error, there might be faults. So idea in software testing is to uncover faults, right? So if symbolic execution is trying to execute all paths, then eventually it will also be able to reveal some faults, and thereby I'll be able to fix it, right? So this also automates the process of creating test cases. Okay, because otherwise you have to create test cases on your own, right? So this to some extent helps in creating test cases as well. And we'll see the shortcomings also, and like why we are not using it all the time and so on and so forth. Okay. But that might be a discussion for another day. I'll just go through the specific aspects. So basically the idea of reaching something, right? How do I reach? So you've got a very large function, then so many things are happening there, complicated function. Then what should I put so that I reach a certain place in the program? Like, how do I reach the about statement, for example? That is there. So we'll go by the example. So this is what happens, right? Typical case. You have a method, something's happening, after that is going to return something. So the normal execution, what happens? We are trying to contrast it, right? So when you give a test case, right? So I have given 135. Now what is going to happen, right? So so a statement by statement we have to trace it, right? first statement XYZ are not there, ABC is being defined, so ABC is taken from here, right? And so on. So something happens after statement 2, X is 4Y, because X is equal to A plus B, right? So this all this happens, right? So A plus B is 3, and so on and so forth. So after every statement, whatever is happening, you're noting it down, right? After that, after all of this is done, in the last statement, number 5, you're going to return 9, because on this input, we know that this is what is going to happen. Okay. Now, in symbolic execution, on the other hand, we are not putting concrete values for the inputs. Rather, we are having symbolic variables. So this is what is known as symbolic variables or symbolic inputs, right? So A is alpha 1, right? So this is like that. Alpha 1, alpha 2, alpha 3 we are providing here. It's ABC, alpha 1, alpha 2, alpha 3. And then we are again tracing it, again tracing it. So first statement, what happens, right? So we are providing it, right? So this is provided by us, alpha 1, alpha 2, alpha 3. PC will come to that. PC is true, so we go ahead, and X is alpha 1 plus alpha 2, because exactly that is what was happening, right? B plus C is that, A plus B is that, right? A plus B is alpha 1 plus alpha 2, so that is what is happening. It's just that instead of trying the concrete state, trying to trace the concrete state of the program, you are also doing symbolic execution, and tracking what happens to the symbolic expressions, right? So you are having symbolic expressions now, instead of some value that is there. You are having a formula, so to speak, right? That is there. So this is the symbolic execution of this method. Now, PC is path condition or constraint. We refer to it as constraint generally, path constraint. Okay. So now we'll come to know what path constraints are. Path constraints are basically what conditions are necessary for you, for the program, for the execution path to reach some place. What should happen, right? So for example, if I want to go to error, right, then the first condition should be true. I am not concerned about the input at this moment. I'm just saying that whatever is at number 6 should be true, right? Then only I'll go inside. So 6 and 7 should be true, right? Both of these. If both of these are true, then I'm going to reach there, right? This is one reachability aspect. Like, how do I reach? So then symbolic execution is also trying to trace it, right? So I provide this. Not when you trace, the one thing that you have to keep in mind is when you are doing this tracing, no, you have to be careful about what all is happening in the program. Just jump straight to the conditions and think like that. Okay, you have to trace one by one. So you go to this statement, you see that y is being provided as input as to twice, so therefore I go here. That's what how the program is going to behave, right? So you go to the twice statement, and then 2 into whatever variable is there, so 2y will happen, and then you're going to compare with 2y equal to x. Okay, 2y equal to, is that the case? Then if that is the case, then I'm going to go inside. If that is not the case, then I'm not going to go inside, and so on and so forth. If that is the case, then I go here, so I'll go to the number 7. If number 7 comes, then I'm going to check for what x is greater than y plus 10, and so on. So if that happens, then I'm going to come inside. So this is the condition that you get. Okay,
So
this is x naught. Go ahead, please. Yeah.
yeah, so symbolic execution at line 7 is this one, right?
Yeah, symbolic execution at line 7 on. So there is no concrete input, by the way.
Yeah, yeah.
This comes, yeah, I mean, here is just symbolic execution. There is no concrete status. So there are two variants of two I mean, see, concolic testing is an upgrade. Okay, so one thing is symbolic testing. On top of it, we are talking about concolic testing later. Okay, so there we'll think about what the concrete state has done, and then we are going to how symbolic is going to continue, and so on and so forth. Here we are talking about pure symbolic testing. Okay, so there's no concrete value as such at this
Yeah,
point. Okay,
so
so we are just talking about constraints.
yeah. So we'll
So to reach
at
this,
7 we have to consider 6 and 7 both condition.
yeah, then you go inside. Yeah.
Yeah.
Yeah, that is what will happen, right? So nested if is like an and, right? Conjunction and. So first thing,
Yeah, yeah,
and
yeah.
this. Okay, so that's why you get this, and this, there's the typo. I think this is x naught, not x plus 0. This is x naught greater than y naught. Okay, this is the condition you have, right? So this is the other condition. Okay, x naught greater than y naught plus 10. So this, if both of this entire thing, right? This is the PC path constraint. If this is solved, so what does it mean to solve a path constraint or any predicate for that matter? These solvers, the SAT solvers, they give you values. So you give formula, they give you values, so that if you put that back in terms of x naught and y naught, no, these variables. So if you put that back, this formula will result in a true. Like this will become true. Like you want to solve it. Solving means what should you put so that something becomes true. So if I say x is equal to 10, like that is a predicate. For example, I'm just saying it, right? So one solution could be that there's only one solution, right? So I have to give 10 to x. I give 10 to x, then that formula will be satisfied. It will be true. Right? So that is what it means to solve something. So the idea in symbolic execution is to leverage the idea of solving constraints. So if I have this constraint, no, whatever is highlighted, if I solve this, I'll get something. I'll get a value, right, for x naught and y naught, such that now, since the way I've done it, such that if I put that back, once I solve it, I put that back, I am sure I'll reach this error. You see, because I've traced it, right? I've traced it like this symbolically. So I know if if these things happen, whatever happened, no, if these things happen, then I'm going to reach the error. Okay. So then I solve for it. I get the values in terms of x and y, concrete values, actual values, numbers. I get it, and I put it back. If I put it back, I'm sure I'll reach the error. Okay? So that is how it helps in a nutshell, in reaching several places. Not necessarily an error. It could be anything, right? You want to reach a particular statement. How do I reach it? Then you do symbolic execution, figure out the condition, solve it, and then give the test case, concrete inputs. So the solution to this will be the inputs to x naught and y naught in this case, such that if you provide it, it will be solved. And if it is solved, like if it is true, this is true, this condition is true, then you know the program is going to follow this path. Certainly, right? Because if I come in and this first case is true, then I'm going to go in, and the second case is true, I'll come to the error, right? That is what is going to happen. And therefore we could go anywhere in principle, right? Could go anywhere, because we just have to solve the path constraint for wherever we want to go and get the values, put that back, we'll reach there. That is the idea. Okay, so this is what happens. Symbolic execution, when it happens, it exercises all paths algorithmically. So start with the, I mean, of course you have to look at the decision nodes, right? Because that's where the difference may come. See, if it is all linear, then there is no choice. Like, how do you exercise? There's no notion of a different path. Like, it's linear, like it's like a chain, right? For example, then you're going to just start from the initial node, go to the final node. There's no choice, like where to go. It is already decided that you're going to follow this path. But if there are choices, then you may go into a different path. If you may venture into a different branch, and so on and so forth, right? But typically in real world programs, you have lots of branches, lots of paths, lots of possibilities, right? In large programs. Now, what it does, it just starts collecting the path constraints every time it hits something, right? So it starts from this, it is going to collect that, and then it is going to solve it in two ways in terms of solving it. One is that how do I make it true? Okay, so if it is true, what happens? Then I'm going to collect it, and so on and so forth. So for as long as you are getting conditions, you'll keep collecting it. But so and the other case also you'll solve it. So if you want to, like the true case, if you follow, then this is the condition. We'll come to that later. But if you want to make it false, then you solve you solve it, and the negation of it, rather, this will be the true case, right? If this happens, then I'll go here, right, the right branch. But if it is false, then I'll go here, right? So for the false case, I have to provide this. So this is the solution. So I'll get this and negate it. 2y not equal to x, right? So these two values, right? Here 2y will not be equal to x, because x is 0, right? 2y is what? 2y is 2, x is 0. So therefore this will be false, and I'll reach this part, right? So here the notation is slightly unconventional. What we are saying is that uh, for this to be false, I need this value. This is a solution. One solution, one of multiple solutions. This is one solution wherein this will turn out to be false. How to make it false? Okay. Now, if it is true, if it is turning out to be true, then I'll encounter another condition. Another path constraint will be there, right? So I'll add it, of course, with the existing one, right? This and that, because this is already true. So I mean, right? First have to be true, right? So and this and that. So I'll solve for both. Now this thing is exactly that. This one. Okay. So you solve for, rather, this one is that. Okay. So this one is the negation of this. So this says true false. This says that for the first condition it is true, and the second condition is false. Okay. So if you want to follow this path of true false, this sequence of true false, then you have to put this value. This is solution. This is a solution. How do we arrive at this solution? By negating the second condition, keeping the first one as it is, negating the second one, which is x less than equal to y plus 10, and then added a conjunction in those two conditions, and then solved for it. So when we solve for it, we got this. Now if you put that back, and you can do it here also, if you put that back, substitute it, you'll see that the first one will become true, second will become false. If it is false, you reach here. Okay. And similarly, true case also. So for true, maybe for example, this might be one input. There could be other inputs also which are following true case, other inputs which are following true false case, or maybe the false case above. Yeah, there are multiple inputs possible, but one solution it gives, one of the multiple solutions it gives, so that if you put that back, you are going to reach that particular statement in the program. So that is the idea of symbolic execution, and that is how it helps in reaching certain places in the program, because you don't have to manually work out like, okay, I'm providing this, so I'm going here, then I should make it like this and so on and so forth. Like, it involves a lot of manual analysis otherwise, right? If you do it in with symbolic execution, you are trying to do it like automate in an automated fashion. Okay, you're doing it all at once in some sense. Okay, so there's this idea of program proving also. Like, the idea is that, okay, so when I like assume theoretically that I'm doing it for all possibilities, of course it is infeasible for large programs, but I'm just saying, right, it happens that I've done for all of the things, then I've essentially proven that there is no fault in my program, right? But that is impractical to do. But I'm just saying theoretically it is possible, right? If I do all that, then I say that, okay, I've exercised all possible branches, I've seen everything, and there is no error. Like, everywhere I went, it behaved as it was supposed to behave. So there is no error. I could say that, right? But that will be like a proof. But that is difficult to do in practice. Like, because formal methods are involved, right? You have to just make everything formal, which is difficult. Like, in practice, very large programs. How do you come up with predicates for everything? This is not possible, right? And there's this. Internet also involved, right? So you're sending requests, network requests are involved, and so on and so forth. How do you know what will you do, like what will the server respond with, and so on. So in practical situation it is difficult, but some portion of the program, no, wherein specifically wherein you have uh, embedded systems, that there we try to do formal methods, right? So basically proving that, okay, whatever I have is actually proven to be correct. It is different from testing. Testing says that, okay, I'm providing these many inputs, and I'm just checking from based on which test cases I have tested whether it is correct or not. But formal methods are different. It is saying that I'm proving it. Okay, regardless of whatever input comes, I've proved that this is correct. Okay, so some portions of the program could be proved. Okay, but not everything could be proved. Okay, so therefore you have to come back to the usual testing, by means of test cases and so on. That's what we are doing, right? In practical situation, that is what you have to do. Okay, so program testing is one. On one hand, I'm just giving inputs. Program proving is the other extreme, wherein we say that, okay, I'm not going to check with the input, rather I'm saying that I'm mathematically proving it, that it is correct. So that is also difficult because it could not be automated and so on and so forth. Okay, so that is the idea. But symbolic execution is a practical approach between the two, because it allows you to do some amount of automation, but still you have to do test cases. Like, it solves it for you. It solves the reachability problem for you, and then you know what test cases to provide. Then you have an idea, okay, how good the test cases are, and so on and so forth. Okay, so therefore it says each symbolic execution is equivalent to a large number of normal test cases, because it is actually exercising a lot of branches at once, right? And then you solve for all of them. Multiple test cases will be there, right? You get multiple inputs, and then you provide all that. You know for sure that if I provide that back, I'm going to follow so and so path in the program. Okay, so that's what happens, and so on and so forth. So path constraint is, we've discussed about this. Okay, symbolic state is just a map. It's like a dictionary of keeping track of whatever happens at this moment, right? So this table, if you remember from the beginning, was there, right? So this one, a similar thing we are having. This one is there, right? For symbolic execution, this one is what symbolic state is. I'm keeping track of what all I have at this moment. Okay, is this okay? Now what happens is that it starts with the uh, an execution path is basically a sequence of true false, because wherever it is linear, see, think about it. Okay, wherever it is linear, meaning there is no if condition or loops, then you don't have a choice. You have to follow that linear path, right? You don't have a decision to make, right? Always going to be like that. But wherever you have a choice, you have a choice, like, meaning if condition, meaning true or false, then there only you can make a decision, right? Where to go to left or to right, and so on. So the execution path therefore becomes a sequence of true false only, always that is the case, right? Because rest of it is linear, so you know that whatever is going to happen will happen in only one way, right? So execution path therefore is just a sequence of true false values. So basically, whatever position you are at in, if it is true, then you're going to follow the then branch. If it is false, then you're going to follow the else branch, as we have seen in the example above. Okay, so and once we do that tracing, we come up with the execution tree. That's what we've seen in that graph. That was the symbolic execution tree. Now it turns out there are multiple ways of drawing the tree, so we won't be asking about the number of nodes. Okay, so that is done, and then there's some discussion going on how exactly it works, right? So if I encounter this, if e, this kind of a statement, right? If e, then statement one happens, otherwise statement two. So the PC is then updated, right? So whatever I have seen so far, all the other conditions above this statement, I'll end it with this one, right? So though I'll go to the then branch. Now if I want to not go into that, like I have this if statement, I don't want to go inside it. So if I don't want to go inside it, then I have to negate this e, right? I have to make it false. So if it is false, then I'll not go inside. So this is for the else case. I'll negate it. So what symbolic execution does, it creates both predicates. It creates for the then branch, it creates for the not, like the negation also. Like as you've seen in the symbolic execution tree, the true case and the false case. Okay. So that's how it works. And if the path constraint is satisfiable, meaning it can become true, it is not a contradiction or something like that. There is actually a solution to that. Then you go inside and so on and so forth. If it is not satisfiable or it is turning out to be false, then you go with the else branch and so on and so forth. That's what you do. Okay. And yeah, here it says unlike concrete execution, both branches can be taken. Meaning, if you're doing it with concrete values, no, only one path will be followed, right? But symbolic, if you do symbolic execution, you are following both branches, right? Because you have the predicate for the true case, you have the predicate for the false case also. Depending on what you solve, if you solve it, then you can follow both paths, right? So that's what. And at the end of the day, it will give you test cases only. I mean, once you solve it, you'll get concrete values after all. So then you put it back, you know how to reach it. But then it kind of helped you in coming up with those inputs, right? With the reachability problem. Okay, how do we reach? And so on and so forth. So again, same example, like we are doing on this example here. So we have the symbolic state. Now x is being provided the symbolic variable x naught, y the input is being provided a symbolic variable y naught, and so on and so forth. So we are updating it and so on and so forth. So after line 6, for example, two constants are generated. Line 6, right? One case is when it is true, right? So then case, so where it should be that 2y equal to x. What is the other case? Other case is negation of that. Only two things could happen, right? Either you go inside or not go inside. So the other case is z not equal to 2y not equal to x, right? So these are the two path conditions or path constraints that you get, right? X not equal to 2y not, or x not equal to 2y not, and I'll solve both of them. We solve both of them, we'll get this, right? And one other case is for the above one. For the above one, it is if it is equal, then we are going to follow. If it is not equal, then we'll exit, right? So therefore we have three conditions. Why three? Because if it is true, then you have to continue, right? If you continue, then you got to the other one also. So for as long as you have conditions, you keep collecting it, and making a conjunct out of all these conditions, and then solve it, similar to the formula we have seen above, right? But if this one is false, then we are not going to go inside, right? So we'll straight away exit, right? So there are three cases. So I think this one is the false case for the above one. For the first outer, if this is the false case, this is the true case and the false case for the inner one, and this is the true and true. Both are true. Okay, so these are the three. Go ahead, please.
I have a doubt.
Yeah. Yeah.
So for statement sixth line 6, we had two cases, one negate and one normal case.
Mm.
And line number 7 also we had one true case and one false case.
Yeah, for the inner one, yes.
Yeah, correct, right. So in code, if you see there, can you go to the code once?
Yeah.
So if the sixth line if fails, it comes directly to the line number 10.
Yes.
And if you fail the line number 7 also, it directly comes to 10, right?
If you fail the line number 7 also, it directly comes to 10. Yeah, that's correct. Yes.
Correct, right?
Yeah, that's correct.
Yeah. So
I mean, basically, it will not come to 10. It will come to, I mean, here 9, and then from there.
Basically, it's end of the program, right?
Yeah, basically, yes.
Yeah, it's end of the program, right?
Well, not really the end of the program, because once you exit from the test me function, because you are doing this like we are seeing here.
End of the function.
Yeah. So you come here, and then after that you have to after that also something could happen.
Yeah.
So
So in concolic test cases, we'll give an concrete value. Let's assume 1 and 2. Okay. So in this case, if you see, let's assume 2 and 1, then it will be easier.
Okay.
Let's assume 2 and 1. So 2 equals to 2, it will happen, right, in the line number 6.
2, because twice of y is what? So this is 1, right? So 2. Yeah. So this is 2 equal to 2. Yes.
Yeah. This will execute concrete test case, right?
No. So given the concrete test input 2 1, 2 1 as you said, right? The program path that will be followed is 6. So this will be true. So again, what I said, remember, execution path is a sequence of true and false. Sequence of true and false for all conditions that you face. When you execute. So one condition we know, that first condition we've seen that, okay, so this is 2 equal to 2, so this is becoming true. So the first in the sequence, the first one is true. Now what about the next one? So we have 1, right? No, rather 2. 2 greater than 2 is not greater than, right? 2 is not greater than 11. Yeah, so this will be true false. So the path that is going to be there when you give 2 1 as the
Yeah.
input, the path that is going to be followed is 2y, 2y equal to x, and the other part, and the the logical and,
Yeah.
logical and, what is that, 2 less than equal to, less than, because
Yeah.
that is, this will be the condition.
Negate of 7, right?
Negate of this, yeah, negate of 7, that is, yeah,
Yeah,
less
yeah,
than
yeah,
equal
yeah.
to 1 plus whatever,
Yeah,
10.
negate of 7 will come, right? Yeah, correct.
Yeah, yeah, exactly, this one, yeah.
Yeah, yeah, yeah. And based on this one only, we have to decide the concrete.
Correct,
Three
correct. So there are
steps, right?
two kinds of questions we could ask. One could be when I give the input. See, when I give the input, what is followed? Just straight away, like I have given this, what is followed? So you say, okay, this is becoming true, this is becoming false. So you say that you give that predicate, saying that okay, when I give one and two, two and one rather, this is what is followed. This is 6 and negate of 7. 6 and not 7. This is what happens, right? When I give 2 and. But we could also say, we could also ask that when I give 2 and 1, what is going to happen next? Okay, next at the next execution. So you give 2 and 1, you know that this is true, this is false, true, false. What is the next step for the symbolic execution? Next step is to negate whatever happened, negate and go to the other case, right? So therefore, when we ask for the next case, you give the negation of the last condition, whatever. So the last one is it was less than equal to y plus 10, right? The whatever happened. So the next step would be to negate it and go to the other case. So
Negate
depending
of
on what we,
concrete value.
yeah, no, negate of this condition, the last condition, 7.
No, no, negate of the concrete value, right?
How,
What
how could
you
you how
substitute?
could you negate, concrete value?
No,
Like
no,
concrete
no.
value.
I meant you substituted the concrete value and you got a condition that we have to negate, right?
So the condition that you got after tracing with the concrete value, you negate that. Yes.
Yeah,
That's,
yeah. That's
yes.
that's what I got confused in geos. You got the
Right,
point,
right.
right? Yeah.
Yeah, yeah, exactly. Yeah, yeah, I understand now. So I think you had not traced with the input. Rather, you just saw the condition.
No, I traced with the input, but it told next execution. So I thought it's
Okay.
the error itself.
Current one.
So that line,
Okay.
that question has some ambiguity.
Oh, makes sense. Next.
Next,
Okay, okay.
next
Uh,
generation means that means it comes to next line, right? Generation means next line, right? That's what
no, no.
ambiguity
So
was
in
there.
the,
That question.
makes sense, makes sense. So
That's why
in
only I
terms of,
closed.
okay, makes sense. So in terms of symbolic execution, when we say next execution, it means not the next statement, rather, what is going to happen next in the algorithm. Because you
It
remember one
spells
thing.
next generation, not execution also. Next
Ah,
execution means then we'll go to the next execution means it will go to next loop. That's fine.
okay, okay, makes sense. So we want to say like what is the next path condition for that
It
basically?
is, yeah, it was asking a
Uh,
symbolic generation for the next execution, right? So it was confusing me whether to go to
uh,
line number 8 or the else loop.
okay,
So,
makes sense. Yeah, we'll keep a note of that. I think we'll see if something is
yeah,
going to
you
happen.
can
With
just
some.
note it down.
Mhm.
Might
Okay,
many might have got wrong. I don't know. Might is it?
okay. Yeah, yeah. We'll look at the submissions once and then decide. Okay, so that, I mean, that is basically the introduction of how symbolic testing is working. Now, one case we have not talked about. What about loops? Right? Loops are very common. Loops come. Then what are you going to do? Because loops can potentially run infinitely many times, like in this case, right? So this is just, think about it as like a terminal, like a bash script. So what happens is I'm just having an integer sum here, and then I'm just taking it forever. Or even in Python we can have an input, right? So n equal to input, and then while n is greater than 0, you know I keep taking it, right? So there is no, fundamentally I cannot stop. Like, where should I stop? This is infinite loop, unless the user presses control C, or exits, something like that. You have to manually do something to exit. Otherwise, as far as the program goes, there is no way to exit. Now the problem is, remember one thing: when you are doing the testing, no symbolic execution, the program under test is not running. I mean, the program itself is not running. Some symbolic execution algorithm is driving that program. I mean, it is running technically speaking, but it is not running in the usual way, right? Running in the usual way means I have a code, I'm running it directly. But when I am driving the program through symbolic execution, it is not running in its usual form. It's still running, but so the symbolic execution, the driver, whatever you call it, the test driver, basically, it does not know how to stop, because it is just having access to the source code, right? How does the program know when to stop? Right? That is the halting problem, which is NP complete. Again, that will be a different discussion. But we cannot, just by looking at the code, we cannot say if something can be stopped or not. Okay, that is the key idea. Okay, so therefore we need something to make sure such cases do not occur, that I'm stuck. Otherwise, I'll be stuck somewhere, right? So therefore, we have a very specific way of putting loops into predicates. Like when you do so, when you are, because of course we are having path constraints again in this case also, but we have to have a specific format for that path condition. It says that we have to follow something, right? We have to have a limit. So therefore, this is the notation we follow. We say that okay, so this is the loop. Of course, if it's an infinite loop, then you don't know when to stop. Like potentially it could run forever. So the idea is how do we stop is to give a number n such that n times I'm going to go inside. N times I'll follow the loop, whatever loop is there. N times I'll follow, and then n plus one time, the last time, I'm going to exit. That is what the convention is, because this makes sure why we are doing this. We are doing this to make sure that we don't get stuck, because then we cannot get stuck at all, right? Because we have a finite number of iterations to follow. You say 10 times I'm going to follow this, that's okay, and then the 11th time I'm going to exit. So what happens, how do we write it then? And this, by the way, and I belonging to 1 to n is like summation, right? Similar to how you do summation of I to 1 to n, from I to I equal to 1 to n. So similarly, and is like you're doing, and all the conjunctions for all conditions, that's what you're doing, okay, here. So why is it written like this? Again, this is dependent on the code, okay, on the code. Be careful with that. So since in the code, to go inside the loop, to follow that, to do one iteration of the loop, you have to have the condition as n greater than 0, okay. And to not go inside the loop, what you should do, negate it. So n less than equal to 0. So then what will be the predicate? Predicate says n times true condition, okay. What is the true condition? Ni greater than 2. Ni will be such that this greater than 0. This condition is coming from directly from here, okay. I'm making it true 10 times or whatever times, right? Small n times, small n is given, right? So n times it is true, and this is a requirement, we'll have to have it, right? A false case. The last time, so 10 times I've done it, the 11th time I'll make sure whatever I give is turning out to be false, like it becomes false. So when it becomes false, I'll exit. This will make sure I'll exit. So this is the less than 0 case. So this is coming from this while loops condition actually. True case is n greater than 0. So what will be the false case? False case is negation of that. Therefore, this is the negation of that. Okay, so this is the path. This is how you write a path condition or path constraint for a loop, for any loop whatsoever. Okay, so this you have to be clear about. Okay, so it says 1 to n. So you have to count it, like how many times is it correct or not, and so on and so forth. There could be questions on this. Okay, how many times we are going in, this could be a question. Okay, how many times we are going in, so what is the correct notation, how do we write it? Okay, because if there are loops, yeah, how do you come up with path condition? That is the idea. So this is the notation, this is what we follow, this is the idea. Okay, now one more thing. So after this is done, after that, like after everything is done, what is your symbolic state? Because remember, we are tracking that, no, we are tracing it, we are tracking everything, like where we are and so on, right? The symbolic values and so on. So at the end of the execution, we could ask what is the current state. Okay, so again, from the program, you have to go back to the code, you have to look into that and then decide. So that n, the value of n will be the last n that was provided with which I exited the loop. Certainly, because after this I exited, right? And once I exited, nothing happened. Again, if somebody is replacing n here, something else could happen. But here in this program, we see that after that it ends, the program ends. But it could be that n is replaced. But in this case, we see that we know that it will be the last value only. Once it is ended, the n will be holding the last value of whatever n was provided. Sum is certainly, because what we are doing here, again, you have to see sum equal to sum plus n. This is the sum and n we are talking about. Okay, so at the end of the execution, n will be the last n with which we exited. Certainly the last value of n with which turned out to be false, so we exited, must be a negative number, right? The last n must be a negative number with which we exited, and the sum will be the sum of all n's wherein we followed the loop, not the last. This does not include the last n. Okay, only positive values, right? So therefore we say n is the last n, which is n plus 1. N times we went inside, right? N truths. So n times a sequence of n truths. This is execution path, right? N times we went in, so n times you have the sum, because every time we went in, we added, right? We went in, we added to the sum, we accumulated that. So n times we did that, and n plus 1, the last n, one after that, to the false case, is what it is holding. So at the end of the execution, this is what your state is going to be. N will be the last value of n, and sum will be all the sums before the last value. Is that okay? Make sense? Any confusion there?
I have one question.
Go ahead.
So we gave like I belongs to 1 to n, right?
Hmm.
That means naturally it's n values being assigned from 0 1 to n times,
Hmm.
correct, right? But actually, normal case n naught will be assigned, right, default.
No, no, yeah, yeah. Normal case it will be assigned. So the thing is, yeah. So other notation is that when since here we are starting from one, no, one. So 1 to n is how many numbers? N numbers, right? But if you say 0 to n, that will be wrong because 0 to n is n plus 1 numbers, right? How many numbers are there? In 0 to 5. So 0, 1, 2, 3, 4, 5 are 6 numbers, right? Not 5. And since this is a set, this is an inclusive interval, right? So
Yeah,
you are saying I belonging to 1 to n meaning n numbers. So if we start from 0, then you have to say n minus 1, and that's what we'll do. The correct notation will be I belonging to 0, comma n minus 1. And then n sub n, this plus 1 you'll remove from here because n minus 1 up until n minus 1 you're going, right? So 0, 1, 2, 3, 4. So that are 5 values. So 5 times I want to go inside. So I'll have 0, 1, 2, 3, 4. And 5, the n5 will be this false case. Okay, you understand what I'm saying? N.
yeah, yeah. But so in question, will they mention like n truths itself or
Yeah,
n?
yeah, n truths. Yeah, yeah. Generally, we'll mention n truths only.
Okay, so if they mention like n minus 1 truths means we have to use that case, right? 0 to n
Yeah.
minus.
No, 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 no. If you are starting from 0, then this interval goes up until n minus 1 only, right? Is that
So
part
if
clear?
you, yeah, 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 if you go to the program,
Hmm.
so there we have this given a symbolic input.
Hmm.
Okay,
Okay.
that we don't know whether that's an 0 or 1. Okay, we assume
No,
it
no,
to
no.
be
We are not
1.
talking about that one. Okay, okay. Sorry, sorry, sorry. I
Uh,
think, see, this n is not that n, okay? This capital and small n is different. We are talking about one plus
no,
small
no,
n.
no. I am saying capital N.
Hmm.
In our case, we want to have it to be greater than 0.
Yeah, n
That's why,
times.
yeah, 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 in times.
Okay.
Correct, right. So that's why we are setting first value to 1.
Yeah, yeah. I mean,
Okay,
whatever
yeah,
you said, if you want to set it to 0, also it's fine. The thing is, you
yeah.
have to make sure that in that set, and this is like a set, right? Interval. In that interval, n numbers are there. Just make sure that whatever interval you choose, okay. You can as well say 3 to 10. 3 to 10. Now, how many numbers are there? There are 8 numbers, right? So if
Yeah,
this one is 3, 3 comma 10, like how many numbers are there? There are 8 numbers, right? 3,
yeah.
4, 5, 6, 7, 8, and 9, 10. There are 8 numbers. So
So
if there are 8 numbers, I'm going to go inside 8 times. That's what happens. Yeah, go ahead.
sometimes that index changes from 0 to n minus 1. Sometimes it's 1 to n. Both are correct, basically.
Yeah, both are correct. The thing is, how many numbers are there in that interval? You have to make sure that. Okay.
Yeah. So
Uh,
it does not depend on the condition itself, right?
no, no. Yeah, this interval, the smaller the
Small interval.
it does not depend on that. The capital one, whatever the condition is, that is
Uh,
of course the condition. But and this one does
yeah.
not depend on. Yeah. Okay.
So in some
Uh,
previous year question paper, it had 0 to n minus 1 and n of n we had.
Ah,
We were confused because condition was equal to 0.
No, no.
ah,
Condition is basically, see, ni, it can be only two things, according to me. Either it can be greater than 0 or it can be equal to 0.
less
Like,
than equal to. Yeah.
yeah, if it's greater than 0, it means it's true. Otherwise, it
Hmm.
means it's false. There are
Right.
only
Right.
two conditions.
Hmm. The small n is how many times you want to like
Navigate.
how many times you want it to be true. That is okay.
Okay.
Yeah. And by the way, one thing since we are talking about true here, I'll just make sure one more thing. See, it might be okay. It might be that there is a loop uh, that is happening in a slightly different way. Okay. Maybe that example also I'll show, wherein you have a
Do
break.
while loop meant.
Do while loop, but there could be a break also. No? So it is as if you go inside, then you break. If you don't go inside, then you continue. It could be right. It could be like a do while loop. So in that case, you have to be careful about when are you exiting and when you are following. Okay. So when we say true, it does not literally mean that you have to make that condition true. Meaning, if it is less than, you have to, might be that you have to make it false to continue. Also. What are we saying is that you follow the iteration n times. Whatever is happening, you do that n times. Okay. How it is happening, you have to look at the code and accordingly come up with that condition. Generally, it will not be. It will be easy only, like greater than, less than, all such cases. Okay. For example, if I say while, and forget about that greater than 0, I say while n is prime. If so I'm taking numbers, arbitrary numbers I'm taking from the user, maybe, or symbolic input I'm taking. I'm saying while n is prime, you keep doing that, right? So I'll have to, and I say I have to do 5 times. Then I need 5 prime numbers, right? Then only this condition will become true 5 times, and then I'll go inside, right? And then some 5 prime numbers like that. But if something becomes composite, immediately I'll exit, right? So I need 5 prime numbers. That is the idea. Like n truths meaning, how many times you want to follow it, and it depends on whatever condition that is. Uh, how do you make it true is up to you. Like, you have to see the code. Is This is just one instance of the expression. It could be different also. But it will be easy. You can figure.
Sir,
Go ahead.
I have a question on this concept related, and I've
Mhm,
encountered a question in the PYQ in the same
mhm,
concept. I
mhm.
mean, can I share the question now,
Yeah, please go
or
ahead. Go
should I
ahead.
do it
Yeah,
after this? Okay, so
yeah.
I've
I mean, I
shared it in
mean,
the G chat.
yeah. Okay, if you share that, then I'll go through that. So a few things I'll just mention. After that, I'll exit. So
Okay, sure, sure.
this is one part. Yeah, I'll go to your question also. That's okay. Thanks for sharing. Okay, so then that is done. Yeah. Again, same idea that we mentioned, right? It could contain loops, so it might result in an infinite number of paths. We know that, right? So we have to have a termination condition, right? So that there should be some termination. So that's why we add this last case saying that no, after you have done this so many times, then you make sure you exit also. Otherwise, you keep doing it forever, right? So you have to have like this followed by a false. False meaning with respect to that condition, whatever is given. How do you make it false? You negate it, right? You negate it, make it false. Okay. So limit. That's how we put a limit, right? N becomes your limit now. 10 times, 20 times, how many times you want to do that. Okay. That is done. And again, so we come back to the satisfiability problem upon which we've touched upon, I think, previously also. So this is NP complete. This is difficult to do in general and so on and so forth. That's fine. But there are SAT solvers which do a very good job of solving very very large predicates. Even having thousands of predicates to some extent. But again, still difficult for problems to do. Rather for computers to do this problem. But because this is the possibilities are exponential, right? So you have the algorithms which solve this is in analytically solving it requires exponential time algorithms, if you understand what I mean. If you're coming from PDSA, you might be able to relate it. So this is NP complete problem. You don't have a polynomial time algorithm to solve the satisfiability problem, and therefore the SAT solvers, how do they work is they employ some heuristics. It's not an exact solution, rather it is following, making a good guess, so to speak, right? That's how they work, and they work very fast. But again, it is still in NP complete is not proven to be. There's no polynomial time algorithm that does it in polynomial time. If you do that, then because 3 SAT comes from here only, and if you prove that 3 SAT is in P, meaning there exists a polynomial time algorithm which can solve these predicates in polynomial time, not in exponential, then you might have solved a very problem of a very high consequence in computer science actually. So that is still not done to this date. Okay. So yeah, the other problem, the other advantage is that it could be that some constraints I have encountered, right, and it could not be solved at all. So I say a equal to 10 and, so I have a conjunction, right, saying a equal to 10 and a not equal to 10. Now this is, I mean, this is like this is a contradiction, right? It cannot be solved. But constraint solvers are smart enough to figure out when something is not solvable, like meaning it's a contradiction. So they'll report saying that it cannot be solved. That is one part of it. The other part is feasibility. Even for path, so if very involved predicate is there, now even for the constraint solver, it is not possible to do it in reasonable amount of time. Like how long would you wait then? Because I said it is exponential time, right? It might take a very very long time to solve it. Then it becomes difficult, right? So one case is when it is not solvable because it is a contradiction. So in that case, they'll report saying it is a contradiction. So that is also fine. But if it is solvable, but or you don't know whether it is solvable or not, but still it's a very long predicate, so you take a very long time to solve it. So then that becomes a problem. Okay. So this is one of the disadvantages. The other very common disadvantage is, like very apparent disadvantage, is that you have functions which are being called which is not there. Can you think of one such case? So even this web, right? So you have web browsers and so on. So they call other things, like I give URL, something is getting downloaded from other client and so on and so forth. There's communication happening, client server, right? So you don't have the entire thing here with you in the program that you're doing symbolic execution. Not everything is there. You cannot infer everything. You cannot make inference. You cannot do inference, right? Because you don't have everything. So you have a dependency on something external, which is not there. So then how do we come up with path conditions? Because you don't know what is there. It's black box for us, right? So therefore it's a problem again. So concolic, then this is symbolic testing, by the way. Concolic is trying to alleviate this one. The second part is trying to just kind of work around this. There's a workaround in concolic basically that helps you overcome this limitation. Okay. And the third case is it's not a disadvantage as such, but we could consider it one, like very long paths, right? Again, huge number of paths. Because symbolic, what it says is I'm going to do every path, right? I'm just following every execution path. So if you have huge number of paths, again, it might be impossible or infeasible. That is one, but we could put a limit on that. But if you put a limit, then it is no longer symbolic execution in the true sense, because that's it. Like by definition, it's trying to do all paths, but again, you can have limits similar to what we do for loops, right? I mean, it does not make sense to keep on going forever, so you just put a limit. Similarly, on the paths also, you can put a depth, some depth, right? So I'm going to go up until this depth and then I stop. Okay, so some depth, because again, it's not practical to have uh, very long paths. Okay, so this one we'll see. Second one is mainly the second point is what concolic is trying to help with. Okay, these two are fundamental limitations. I think the first one is like if it is not solvable, it is not solvable. You cannot do anything about it. And this one also is like if the program is large, and I mean you cannot do it like it is not feasible. It is not feasible. You cannot do anything about it. Maybe you can put a limit. That's okay. But again, that's about it. This one is again it's like a workaround, but this one we are trying to alleviate a little bit with concolic testing. Okay, go ahead. I think somebody had a question. Uh, any question? Okay, I think it's fine. Yeah, so I'll not go into concolic in detail, but basically that's what Dart is. I just mentioned the distinction. So symbolic, what happened is I started with a symbolic variable, right? And then I trace the program. I see where I reach, where I don't reach. I solve it. I solve all of it. I get the test cases. I get the inputs, right? So that I put them back. I'm going to follow the exact same paths respectively. That's what happened in symbolic because I just did for all of it. Now we saw that it's slightly difficult. Like it is becoming impractical to because combinations are exponential again, right? Because you have what is the execution path? True, false, right? So one condition is true, the other is false, and so on and so forth. So that is also exponential. So it's difficult to do in practice. So therefore, concolic, what it does is it starts with some random input and then executes it. It kind of drives it. So it's like a smartly. You're still doing concrete execution, but doing it in a slightly smart way. Okay. So that's what Dart is. Okay, concrete plus symbolic, it does both. So you have two states now. You have a concrete state as usual, no? The test cases that we do by hand. Symbolic. So you have a symbolic state that we have seen and concrete state also. So normal notion of state of a program, like the usual state, right? We have put in variables, integers. So x is equal to 1, y equal to something, and so on. So this is so what it does. The difference is now symbolic was starting with the condition itself, like on the program, it kind of analyzes it and starts with the condition. Here, concolic is starting with a random input, and that is the primary distinction. Here, we'll give you an input to start with. This is the beginning, okay? So I'll give, let's say this is random, totally random, okay? So I start with x is equal to 22. This is coming from the same function, actually, the test me function, okay? So x is equal to 22, y is equal to 7. Then the program is executing both concretely and symbolically. Symbolic execution is still happening in parallel, but I'm also parallelly doing concrete execution. The actual program is also running, okay? Now we see what happened in the concrete state. So we see that when I give this value, and we can go back to the code and check that, we see that concrete execution has taken the else branch. Okay. So then whatever happened, no, we'll observe it. In the concrete state, whatever happened, accordingly the symbolic execution will generate the path constraint. So since the else case was there, right? So x not equal to 2, y not is the condition, right? If there is condition, if condition, the first one. So since I have followed the else branch, so corresponding to that, I'll generate the PC. Corresponding to whatever happened in the concrete state, right? So since this was the case in concrete state, I generated this, right? And I'm going to then negate this because the concrete state followed one branch. I need to go to the other branch. So then I'll negate it. So I give that, this happens, I negated it, I got this. So this will force the program into a different execution path. You understand? So in the symbolic one, I was just doing starting from the predicate, but here we are starting from a random input. Whatever happened, accordingly we'll decide what to do. So if it is true, then I'll make it false. If it was false, I'll make it true, and so on and so forth. Okay. So this happened. Now so this was not else case, no. So this is the then case. The then case, I went inside, and after that again another condition came in. The nested if, the other if is there, no, two ifs are there, and then this. So the second one also will negate it. Uh, you know. Yeah, this is again concolic execution is generating this, and we'll negate it. So this one is with us now. The last condition, whatever the last condition, negate only that. Okay. So you negate this and you get this, and we will then solve it to get this one. Okay. So that is one. So starting from this input, we had given this is already covered. We negated this one, so we got this one, and we negated the inner one also, so we got this one. So all three paths have been explored. But it is not necessary in concolic execution that you're necessarily going to follow all all branches, because it might be that while you are doing that execution, no concurrent execution, so you start with the random input somewhere, I land upon on the program, and then I am just following it until the program ends, right? So it might be one path only, one, say I reach the end, but the other path might not be followed, right? Because there might be two final nodes, two terminal nodes, no? In the CFG also there might be two endpoints, right? So I had I finished at one terminal node, but it might be the other case I did not follow. It might happen, right? Because I was starting randomly, so I could land upon anywhere. Small programs, that this will not be apparent, right? In small programs, this case, all three executions, all paths have been explored, but this is not general. Large programs, it might be that. Even symbolic execution in large programs might be difficult, but that's the idea. So the only difference is we start with the concrete input. Now, what are the questions that could be asked? We could ask, if this is the input, what is the path constraints to what is the path constraint at a particular line? That was the GA question, right? At a particular line. So we see whatever happens. We'll have to trace it by hand, and then see whatever happens. We'll give that condition. What that is what happened. No, next we say next. What happens after that? You know. So then we'll have to give the other case. So we say what happened in the concrete execution. According to that, what is the path condition? So you give this one. Whatever happened, and then we say next execution, what will happen is, so you have to negate it and give the other case. Okay, what will happen next? So this is what happened with concrete execution. Now this is going to happen. Okay, so that is the distinction you have to keep in mind. Okay, that's all. This basically you have to steer the program. Right. Yeah. So again, this example is done on this. So this is one. So what happens is we'll start with 2634. Now we have to see. Right. So 26 is certainly not equal to 34, right? So this is true. This one's true. But if this is a different input, it could be false also. So I'll straight away exit. And I get this. So these are the predicates and so on. So this is true. Yeah, this is the true case actually. See, because the condition itself is not having not, right? X not equal to Y means this is the true case. This is the true case. So you're going to go inside, right? So you get this condition. So you have to be very careful about when you're, that's why I said, right? What is an affirmation? What is a negation? You have to be careful about that. Because here the condition itself is not equal to Y. So this means this is the true case. Okay. And then so when it is true, I'm going to get this condition, but this apparently did not happen. So I'll negate it. I'll get the other case also. This is the other case. I think 2 is missing here. This is a typo. 2 not equal to x not plus 10 is the condition, right? 2x not equal to x not plus 10 is the condition. So 2 is missing here. Okay, this is the negation of that. This one is the negation of this. Negation is this. Okay, the last predicate we negated, right? That's what we do. And so once we do that, we'll reach the about statement. Okay, that's what happens. Is that okay? Any questions? Okay, I'm assuming it's fine. So yeah, there's some discussion about what kind of solvers are there and so on and so forth. So for all languages, I think most of it you have languages. Again, we had done a detailed discussion, in the earlier terms also, wherein we've gone through all of that. So you can go through the recording if needed. But the questions will be mostly around this. What kind of constraint is generated? What do you need to do, to negate it, and so on and so forth. How do you reach a particular statement? These kinds of questions could be there. And one more thing, the loop. The loop. How do you write the path condition for the loop? For n truths, or how many ever truths it is given, right? This one and this one also. Okay. All right. So that is from week 7. Yeah, week 8 is also okay. There's some formula and some ideas that you need to remember in week 8. I think we had done this also. This has been discussed as well. So you can go through the recording if you wish. And on 31st, we'll go through. Maybe we'll take questions from this one. Try to solve it from one of the PYQs. So that'll make the make the concepts very clear to you, all of you as well. Okay. Yeah. Any other question that you are having? Partially. Okay. By the way, how many of you understood ISP? Like most of you, I think. I hope there's no issue in that. Have you gone through the previously taken live session also?
I am still watching the lectures of it.
Oh, watching the lectures of Wicked, is it? Okay. Okay. Fine. Yeah, yeah. You can go through the lecture, and then again the recording for the previous live session is also there. Okay.
I
So
think
you can go.
it's easier, little bit easier.
This one is black box, no? So this is only talking about requirements and so on. So this is like up until week 7, it was all white box. So we thought about the source code and what all is there and so on and so forth. We tried to create models of it and then done coverage on that. Week 8 is more like requirements and functionally is it correct or not and so on and so forth. But again, some ideas are there about which you need to be clear up until week 8. So basically 1 to 8, week 1 to 8 is your syllabus for quiz 2. So I think the first 4 week is mostly what is already has been asked in quiz 1. Okay, data flow graphs, def clear paths, due paths, all of it you have to be clear about. Some integration testing also, FSM, and yeah, week 5 and 6, all of us I think are okay at this point now. Active and inactive, logic coverage criteria, basically that's what it is, right? And then week 7 and 8. So week 7 is all that I had covered already. Like it's just about path constraints and conditions and so on. So symbolic execution mostly. Week 8, you have to remember certain things. Okay, so this is black box. This one we can go through in the next one. Is that okay?
So
Hmm.
yeah, so I
Go
have
ahead.
a doubt. So in
Hmm.
week 5 and week 6, we have a NOT gate operation, right, to find out P of A or something.
XOR gate. Yeah, yeah.
Yeah, XOR, so not gate, XOR gate. I find
Hmm.
it little difficult to derive at the final state of it.
Not the XOR table, no? Truth table is that?
Yeah, except
Oh,
truth
oh,
table I know, but there are some cases where A and B, not
hmm.
of not A and B.
No, no. Can,
Like
can
that
you
case,
can you
yeah.
tell me one condition? I'll just explain that to
Yeah,
you
you can.
also.
Yeah, you can
Uh-huh.
write it down.
Yeah, yeah. Just give me one moment. Maybe I'll stop sharing from here. Yeah, I'll just give me one moment. I'll open up the whiteboard. Yeah, I can show you that. I think it should not be that difficult. Okay, just give me one moment, please. Uh, okay. Is it coming up?
That's able to see.
Okay, thanks. So can you tell me the predicate, please? P equal to?
Predicate I am not sure, but what derived it I can say.
Yeah, yeah. I mean, the condition, no, the XOR.
Yeah, XOR condition I will tell A
Hmm,
and
hmm.
B.
PA is what?
A bracket we have to have bracket. In bracket we
Okay,
had A and B.
okay.
Okay, and XOR.
And outside, is it?
Yeah,
Okay, XOR.
XOR. Then we had not of A,
Okay.
then over condition of B, like that.
Or of?
Or of B, something like that.
Oh,
Or of B. I'm not
or
sure.
of B.
Yeah, it might not happen like this, but I'm not sure what happened there. But like this, some
Okay, okay.
condition
So,
was
I mean, I'm not sure, but because certain cases, what might happen that if you have such a condition, like certain conditions might be that it is not solvable after all. So the entire thing will go to false. It might happen, but let us see. If this is not correct, then it will go to false. But the idea is that yeah, the idea of XOR is if both the things are same, if this is and this is the same, then you are going to get a false, right? Either true or false. If both are true, you're going to get a false. This is true, that is true. So this will turn out to be false, right? If this is false, that is false. This is also turn out to be false only. Okay, so what you have to do, you have to make one operand false, the other operand true. That is generally the idea. Okay, in order to make it true. Okay, and how to make it false, you just negate it. That's a different thing, but to simplify it now, this is what you have now. So this one you have to make true, right? So I mean, we have to decide onto something like
You
at
maybe
least.
this is. Are you sure this is? Correct, correct. I can give another example.
Yeah, it is. I think P of C for P of C it had, not P of A.
Sir, can you take this A or
Please.
B? The predicate? I'm giving you the predicate.
Okay,
Okay.
predicate is
A or B,
A or B.
and this is from a P by Q.
Okay, and
C or D,
okay, very nice. So
and you have to give the anything, do anything, but in the P by Q it is asked PC,
C is it? Okay.
PCC.
Yeah,
Yeah.
yeah. So we'll do for C only. Fine. So what happens is A or B remains and true or D XOR with A or B and false or D. Okay. Simplification rules. I hope all of you know. So it will become what? True will go here. So this will become true, right? This will become true and go away because it's already true. So this true because it's and true. So true goes away. This remains. So PC is A or B, right? XOR this is the first part. The XOR. So this is false, right? So and false. So this is and. This is false. So anything and false will go to false, right? So therefore I'm just simplifying it. The entire thing goes to false. So this becomes this. A or B XOR false. Is that okay? Or do you need
Sir,
little help on the
false or D will become D only, right? Not false.
yeah, yeah, false or B will become D. Oh, sorry. Yeah. Okay. Thanks. Yeah, I'm doing it wrong actually. Yeah, that's correct. So false, actually false or D will become D. That's correct. So this is and D. So you are doing XOR with this, right? Oh, okay, okay. I think that is what you're talking about, right? A or B and D, right? Because D remains. Is that okay?
Yeah. Yeah.
Just let me verify it once again. So A or B and true, A or B and true. So A or B remains. That's correct. I'm doing XOR with A or B and false. So false D remains and A or B and D. Yeah. So actually, this entire thing is your this thing. Okay, now. So the thing is either you have to make this false and this true. So two cases are possible, right? This is true and this is false, or this is false or this is true. These are the two cases, right? Can we do the first case? Anyone would do, right? One or two. So let's try with one. Is it possible? So we make A or B true, A or B true. So this will become true. D will remain. That's okay. That is still possible, right? Uh, no, but yeah. So if I make A or B true, this A or B will become true. So that's okay. D will remain. So D then in the first case you have to make D false. So this is really not D. This part. Okay. And the second case is that I make this false. So if I make this false, see the thing is that if this one becomes false, then this one also goes to false, right? And if this one goes to false, the entire thing will go to false. So the second case is not possible. Is that okay? You understand what I'm saying? I cannot make both sides
Yeah,
false.
at times.
A or B cannot be false because if it is false, then the entire thing will go to false. So certainly case number two cannot happen. So I have to do only with the first one. Now in the first one, A or B is true, so that's okay. So A or B, how will A or B become true? We don't need to worry about that. We just mention A or B because we want to make it true, right? So that should happen. So this goes to true. This goes to true. Just substitute it. Now, so what remains is this true XOR. Once I put it right, once I put it becomes this a true XOR true and D. I have put it right. So I have put it for A and B. Yeah, A or B is true, so this will become that, right? So true goes away. True XOR D remains. So if that happens, I have to make this false, right? So not D, right? So this and A or B was there. I have A or B and not D. Is that okay? It makes sense, right? Hopefully it does. Or if not, I can go over that again. Vasu?
So every time when
No,
we
this I
derive
am
at the end,
this I am very clear. I don't have any issue with
Oh,
that.
you are clear with that. Okay.
No,
Telvin
I
asked.
think as an
yeah.
example. Right?
So every
Uh,
case we will have and at the final condition, right? Like
no, no.
CNF will be
Uh,
there, right?
okay, okay. That see,
Actually,
not
is
less. It
that
could be or also.
operation is correct because it has to be descriptive. It can't be or. It will be usually and. Usually, I've seen that.
So the thing is, see what happens with this, right? So you have A, yeah, yeah. I'll tell you one case where it will not be. So A or B, right, and C. Now you can straight away tell what is PC. How? So this is CNF, right? Remember, this is CNF, right? This is in
Yeah.
CNF. So
Not
CNF,
of
what
that
did
B, right?
uh, no. In CNF, what did we say? To make one clause active, you have to make all the other clauses true. Okay. If you want to make C active, then what do you have to do? You have to make sorry, it's a different pen. Yeah. So in order to make C active, you have to make A or B. I mean, I can go through the XOR thing also. I'm just telling.
Yeah.
So you have to
Negate
make A
of
or
A and B, right?
so no, this will not be negate. I'll give you both cases. So this will be A or B only. This is what you have. And how are we getting there? Okay, so I'll just explain it. So what you have is uh, A or B and true. Okay, just first case XOR. I mean, I need not have that. It's fine. So A or B and false. That's what you have, right? Is that okay? Because C, right? I'm talking about C, PC. So C becomes true, C becomes false. In the other case, XOR I'm doing. So in the first case, true will go away. True will go away. A or B remains. A or B remains. Okay. This entire thing goes to false because and false. Entire thing goes to false. So XOR with false. So this is the thing, right? One side is already false. How do I make the other side true? So the other side being true is the same thing as the thing that is given itself. I mean, this will remain. Right? So this is your
Yeah, understood.
this is your PC.
Yeah,
But the thing that you're talking about is the other thing, right? So you have A and B, uh, yeah, or C. So then what happens is in disjunctive, this is disjunctive. No, this is DNF. Okay, because it's a disjunction of conjunctions. So this one is a conjunct, right? And I'm doing a disjunction here. So this is or. This is or. Okay, so when I'm doing all, it's a DNF, and inside of all the classes inside only and is allowed. Okay, this is DNF, and that's a shortcut that only works with CNF or DNF. If it is purely in CNF, it is purely in DNF, then only it works. Okay, so that happens when that happens. Whenever whatever clause I want to make active, the other clauses I have to set it to false. So if I want to make C active, then I have to set A and B to false. This one has to go to false. Okay, but I could do it this way also. So I have and B, A and B or C. Right, XOR with A and B, or yeah, this one is true, maybe, yeah, true case, false case, right? I'm doing XOR. So what happens is or, so true, this thing becomes true, right? Because this is or. So true XOR and or false goes away. A and B remains. A and B. So you have true XOR A and B. So in this case, when this happens, no, when true XOR something happens, then the other side you have to negate. So you say not A and B. And then you expand with the De Morgan's law. So it becomes not A or not B. Okay, this is your P. What PC still, I mean, for this predicate, this particular. Is that okay? So the idea is very clear. See, true XOR X is happening, whatever X is. Okay, then the result will be not X. That's all. Okay, when false XOR X is happening, the result will be X. The result will be X because this is already false. The one side is already false. So you have X. Okay. And what else? What else could be? Yeah. So the other is that if you have true X or not X, right? True X or not X. This is already. I mean, assume that this is the case. So then I'll have not X because this is already not. So double not will go away. So this will become X. Okay. Or you could have false X or not X, right? So false X or not X will. This is already false. So this you have to make true. This part you have to make true, right? So this will remain as not X. You understand what I'm saying? Is that okay?
sir. So in F case, the remaining will be dominating, and true case, remaining will be negative.
Right. That's what the XOR table says, no?
Yeah, understood. Now this one is clear.
And one more thing. So one more thing, since we're already talking about that. Mm, yeah, I mean, it depends on whatever you have this side again. So if you have, mm, yeah, I mean, you have to decide. So and thing you asked about the and, right? So assume that okay. So one more thing, it might not be constant. So I have A XOR X, right? So what happens is that I could have two. So this one, if you expand, no, it becomes something like that. It could be either not A and X, right? Or because both the cases it will become true, right? Or A and not X. Is that okay? That is what the expansion is. Expansion of AX or X is not A and X. This happens either this happens. This is case one or this is case two. Either of the two cases. If that happens, this will become true. If case one happens, this will become true. If case two happens, also this will become true. Therefore, we have or there. Either this happens that A is negation and X is an affirmation, or A is a A is affirmation is an affirmation and X is a negation. So either of the two happens because what we are saying is that both should not be true, both should not be false. See where it will become false is not A and not X. This will result in a false. Both the things are false, or both the things are true also is not valid. Okay, so these cases X or will turn out to be false. Okay, so you have to have exclusive or, that is what, right? If one thing is true, the other is false. Anyone could be. So expansion becomes like this, and then you can substitute the values and simplify. This one, in this case, it cannot be simplified directly. Okay, meaning if you have something, then you, similar to how we reasoned about here, right? So what's first case and the second case. So either I make this true and that false, or I make this false and that true, right? So one and two cases, we just substitute it and check that from there, right there. Okay, is that okay? Make sense?
Yes.
All right, all right. Okay, any more things, or shall we close for today?
Sir, I want to share one thing. Can I share the
Mm-hmm.
screen?
Yeah, please go ahead. Yeah. I'll stop sharing. Maybe you can go ahead and share. By the way, thanks for being here for so long. I
No,
think.
thanks. Thanks.
Are you able to see?
Okay.
Yeah, I have made a simple logic average and its assumption as an
Okay.
example.
Okay.
I
All
think this
right.
could, yeah, is this clear, correct or not? I just want to verify it. I
Yeah.
find that.
Can you zoom in a little bit? Like
Yeah, I will
do a
zoom.
control plus on that.
No, no,
Maybe.
I will just zoom it like this.
Oh
It's
yeah.
like,
Yeah. Yeah. Okay. Okay. So ACC is where PA is true. Yeah, that's correct. GCC TR for A condition is any pair that has A true A false. Very good. And then for CSC, any pairs that has A true uh, and P true, A false, P false, or A true, P false, and A false, P true. Is that what you're saying? Yeah. I mean, A switching. Yeah. Okay. A switching, P switching, or it could be same also. Telvin. Okay. There could be two more. There's one more possibility, right? A true, P true. Uh, yeah. Okay. That you have mentioned already, is it? Okay. Yeah. Yeah. A true, P true,
I also
and
thought that condition. What you mentioned is first one should be false and second one should be true, right?
uh,
I
that is
I,
also.
under, I understood that even I was confused in that condition, but uh, I think you are mentioning like this, right? False and true, right?
Yeah, yeah, that works. Like because this is not an ordered pair. Okay, this is not
Yeah,
an
yeah,
ordered
yeah,
pair.
yeah, yeah. That also
This is
you
just.
thought right, but in normally when I saw the slides, they are giving order best, not in uh,
Oh,
reciprocal
okay.
best.
No, no, this is not ordered pairs or anything. But see, we go by the row number of the truth table. That is what we do. But in general, you can just have anything. So we are not concerned
Yeah,
about the
yeah.
order.
I thought flipping also will work, but
Hmm.
generally they were taking like straightforward, true and false
Hmm.
only. They were
Okay.
taking.
And for us, what you've written is A is that any pairs that has A true, A false, where each pair will have same minor. That's correct. But the thing is, yeah, P is already true. ICC is where P is false. Very good. For T, for A should have one pair such that, yeah, okay. So pair one, which is A true, A false, while P is true. Pair two is A true, A false, while P is false. Very good. That is your general case. And then you have should have pair one where A is true, A is false, while P remains true. A is true, A is false, while P remains false. P remains false, and where each pair has same minor. That is your eight, row number eight. Okay. So assumption is COC, ACC. Yeah. Uh, 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 uh. Just a second. Just a second. So ACC, active class coverage. Active class coverage is general active class coverage. Okay. So if you mean in the terms of in terms of concept, like conceptually, what is following it? Like there are three kinds of active class coverage. If you mean in that sense, it is okay.
Yeah,
But
yeah,
if you mean
yeah. I mean, in that sense, if they tell whether ACC is covered in COCC, then it's correct, right? Because everything has been covered, right?
yeah, yeah. So no, what I'm saying is, oh, okay, makes sense. So no, COCC is ACC. When we say no ACC, it's better you don't put it there because ACC is
Okay.
equal to GACC. Okay, ACC is GACC itself. Like
Okay.
or else you can make it GACC. That is.
Yeah, yeah. Yeah, I have
But you
written.
have to
I will
change the
remove
order
that. Yeah.
then. Yeah, yeah. Now you can remove it.
Yeah.
Uh,
I
so
just want
now,
to mention that, understand
yeah,
that.
yeah. Okay, the COC certainly covers both. Yeah, that's correct. Now RACC subsumes GACC, CACC subsumes GACC. Okay,
Yeah.
these two you can mention.
That one I have mentioned.
Uh-huh.
RACC has some pairs where GACC is satisfied.
Yeah. Yeah. All RACC pairs satisfy GACC. All RACC pairs. Like for all pairs. Like if you have 10 pairs for RACC, all 10 of them will satisfy GACC. Okay, there's no
Yeah,
problem
yeah.
in that.
Okay. Okay.
Uh,
All pairs. Okay.
all pairs satisfy, right? Because you have the condition itself which is restricted, right?
Okay.
Um, and CACC is all pairs are GCC certified, very good. And then predicate coverage and CACC, yeah. No, what is PC by the way?
So PC
PC.
is predicate coverage and
No, here
CC is
in
closest.
15 you mentioned PC.
Yeah,
Uh,
yeah. CACC coverage subsums PC, predicate coverage.
PC subsumes, but then this after and you mentioned CACC has all pairs. So I think that is only regarding CACC and not about PC because PC has no pairs. Like
Okay.
PC, yeah.
Yeah. Let me do
Maybe
one
you
thing.
can put comma or
I
yeah,
will do
this is
in next
separate thing.
time.
Yeah, yeah,
I will
okay.
write.
And RSCC has all pairs with GCC satisfied. Is it okay? Yeah, that's correct. And now you have GICC which subsumes uh, class coverage. Just a second. GICC. Yeah, up until this is clear to me. Like
Yeah.
GICC, GICC is okay.
Yeah.
Um,
In
yeah,
graph, it's
GCC.
showing like that only. I can see it.
GACC, GICC subsumes class coverage. Is it? Yeah, yeah, certainly it is. Okay, okay. Certainly it is by definition class coverage, And GICC subsumes predicate coverage also. Is it? GACC does not. GACC does not subsume PC, by the way. And
Actually,
GICC, okay, this is a good question. I'm not sure.
no, it
GICC
had
does.
it had that one. That's why. Can you
Oh,
put
class
it?
coverage is okay. Class coverage it does, but class coverage it does. But PC, I'm not sure because it is inactive. So maybe it does. Maybe it does not. Okay, yeah, yeah. So you have, oh, okay, okay, okay. See, the thing is, okay, now I got it. See, the thing is, the general inactive class coverage, even for restricted, the thing is, predicate coverage may not be subsumed always, may not be feasible always. Feasible, I should say feasible. See, by definition, as regards subsumption, it does. It does subsume PC. GICC does subsume PC because you have four cases, no? You have mentioned here, right? Pair one, pair two. So if you do both pairs, you do pair one and pair two, then PC is subsumed. But in some cases, you don't have that pair two or pair one. Either of the two pairs are missing, then you have only P is only one, right? Either
Then
true, true.
GACC is not satisfied itself, right? So
Yeah, yeah. GIS is not certified itself, like
yeah,
partially
yeah, yeah,
satisfied.
correct.
That
Yeah,
is
that's right.
feasible. Yeah, correct, correct. So,
Yeah,
so that's what you say. But yeah, in principle, as per the definition, it does subsume, right? And since you mentioned PC, as soon as PC is satisfied, class. Okay, yeah. No, class is different. Yeah, okay, good. So
yeah.
PC is only there in GICC. That's correct. And RICC is the same thing as GICC. It's just that you
Yeah.
have minor pairs which are same. Yeah, that's correct.
Yeah,
Pair one,
RACC
pair.
does not have any subscription, so it's not there.
RICC does not have because it is inactive, so it cannot.
Yeah, yeah.
What
So
I meant to say rather is that RICC independently also does class coverage because
yeah,
RICC does
I
GICC.
too thought that one, but there is a condition where it can be non-feasible also, right?
Yeah, yeah. So same goes for GICC.
No,
So
no,
what I
no.
see.
There
Hmm,
can be a condition where minor clause might be different, right? Meant.
okay,
Yeah.
okay.
So
So
that's where
it
only I.
also it also comes under feasibility only. Like if you don't have a minor pair, like by definition, it does subsume. Assume that everything is covered. Like when we say about subsumption, we say about the actual condition. Fully a covered case, like not partial case. So when you have a partial case wherein you don't have a same minor pair, then the pair is not feasible, and then it will not be subsumed. That is what happens. But yeah, in general, by definition, it does. So you can
Thank,
also say that RICC does subsume GICC. Yeah, okay, all right. That's all I think. Yeah,
correct.
Yeah.
thanks,
So
thanks
thanks a lot. Thanks a
for
lot,
being
sir.
here.
Take leave.
Thank you so
Have
much.
a good day.
And yeah, we'll announce regarding the session on 31st. Okay, we'll announce regarding that. If
Afternoon, I can
there's
share with you this one. I think it will be clear for you.
yeah, it's okay. Maybe you can put it on. Okay, can you put it on this? Okay, not discourse. Yeah, can you put it on discourse? Maybe you can put it in docs or something and put it on discourse. That will be better. Okay.
I can share it in space or something.
Yeah. I mean, in space is okay, but then if you put it on discourse, that will be better. I think. But
Yeah.
that's fine. Okay. All right.
Yeah.
All right then. All right. Then we'll close. Thank you. Thank you so much for being here for so long. Yeah. See you in the next one. All the best for your exams. Bye.